subscriber before you push?
No, the subscribers have to be functions.
Oh.
In fact, that's what the try-catch was for, to guarantee that they are functions.
Okay. Can you...
Would you just temporarily change the value of publish to something else, but it's frozen? No.
Right, we fixed that one.
I was just trying to think of a way to disable publish inside of this loop. So you just set, you could, you put a var at the top of this that says publish off.
Yeah, we could put a Boolean up at the top which says, we're in the publication mode, so subscribe or publish is turned off while we're looping. That would certainly work. The way I would approach it is I would do an asynchronous solution because I like asynchrony. So there's something that's in browsers and in Java and in Node called setTimeout. And setTimeout receives a function and causes that function to get executed in the future. And you can give it a time which says no sooner than 0 milliseconds from now, call this function. But this function happens in a different turn. So it'll get scheduled after all of the current work in the current turn is finished. So this would cause everything to get lined up in the timer queue. And then if someone wants to subscribe during a publication, their stuff will get added later in the timer queue. So everything stays in order. We're using the timer queue to sort the messages. Yeah.
So you move the publication off into a separate queue that gets processed independently of whatever goes on here.
Right. And it also means I don't need to try catch here now, because if it fails, it'll fail in that turn, but then the system says, well, that turn's finished, and it'll go on to the next one. So everything keeps going. Now, it turns out there's one hazard in this because of a design error in the way setTimeout works. When you call setTimeout, it returns a number. And you can pass that number to clear timeout, and that'll prevent things from happening. Unfortunately, it is an easily guessable number. And that means if the attacker can guess what the next clear timeout number is going to be, he can prevent messages from being delivered by canceling those messages that are in the queue. So we would have to fix that, but we'll fix that one another day. Okay, so those last two exercises are the introduction to the subject of security. And security is a really, really important topic, and unfortunately it's not well understood at any level in our industry. So some people think of security as a war between people in invisible colored hats. They're the white hat guys and the black hat guys, and the white hat guys are probably good guys and black hat guys are probably bad guys, except there are famous white hats who used to be black hats, and black hats who used to be white hats, and gray hats who seem to be playing both sides. And it turns out you cannot easily identify somebody by their invisible hat. That this is a model of security that just doesn't work. Security is not about hats. The thing that's even worse about that model is that it says that security belongs to the specialists. And that model doesn't work. So in the specialist model, it means you've got security experts who are responsible for all the security, and nobody else is responsible for security. And in fact, everybody else is working against the guys who are helping to deal with security, and that model is not effective at all. One consequence of, or one source of insecurity is that things change. It might be that within a limited scope or limited context, you could do things and there's no security vulnerability in doing that, but then things change and the scope increases or whatever, and now suddenly that turns into a big security problem. It is not unusual for the purpose or use or scope of software to change over its life. Rarely are the security properties of software systems re-examined in the context of new or evolving missions. This leads to insecure systems. Do you know who wrote this? I did. I wrote that. That's me. So I'm going to be giving you a set of principles. And most of them are pretty simple and pretty obvious. And once you've got it, you're able to reason about security on your own. The The world of security is incredibly complicated and is always changing, and it's impossible for any human to keep on top of it, particularly if you're a human who has a day job. There's just no way. But the set of principles is actually very small. And if you can understand the principles, you can work out most of the rest of it on your own. Security is not obtained by tricks or hacks. If you ever encounter someone who says, we can secure our system by doing this trick, that person is either misinformed or lying, because it turns out tricks don't work. It's only adherence to principles that works. So one of the first principles for online security of computer systems is that deterrence is not effective. And that's because you can't punish an invisible attacker. Now, in the real world, deterrence is very effective. That's why we have not blown ourselves up yet. But online, an attacker doesn't need to be awake while he's attacking you, so there's no threat you can make to someone you can't see or touch to prevent them from doing things. So the only thing that works is prevention. Prevention is the only effective mechanism. So I'm going to stop here and tell you a story about Johann Martin Schleyer. Schleyer was a priest living in Bavaria, and one night God came to him in a dream and told him to do something. Now, in order to understand that story, I need to tell you an earlier story. Long, long ago, on the plain of Shinar, the world's best architects, builders, engineers, material specialists, and workers got together to build a tower that would reach to heaven. It was the biggest construction project in the history of the world at that point. It was an amazing project, and God was not happy about it. We don't know what his complaint about the project was, but he did not want it succeeding, so he decided to cause the project to fail. And he had a lot of options available as to how he was going to fail the project. He could have caused earthquakes, he could have flooded the plain, he could have thrown thunderbolts down on them. Instead, he decided to go down and confuse their speech. And after he did that, they could no longer understand each other when they spoke. And being unable to communicate, the project collapsed, and they all wandered off and started their own countries. Basically, he created the I-18N problem. So, thousands of years later, he comes to Schleyer while he's sleeping and says, I've changed my mind about that. And what I want you to do now is to create a language that everybody in the world can understand. So Schleyer wakes up and he begins working on his language, which he calls Volapük. Volapük being the word in Volapük meaning world speak. He based his vocabulary on English, but he transformed it so much that it is no help to English speakers at all. That it's hard to see the words world and speech in there, but that's where the roots came from. And he was told that English speakers did not have a problem with umlauts, but I can tell you this English speaker has a lot of trouble with umlauts. But he published his language anyway. He worked for it about a year and then published a book in German about Volapük in 1880. Now, people had been designing artificial languages for many years before Schleyer. There was John Wilkins and Dalgarno in England were doing similar sorts of things. And there have been lots of artificial languages after. But Schleyer was doing this at just the right time. Europe had been in a fairly constant state of war for centuries, and people were getting really tired of it. And they observed what had just happened in the US with their civil war, where new technologies were coming onto the battlefield for the first time, and the terrible devastation that happened there. And they were very concerned that this was going to get really, really bad. And there was a lot of interest in trying to solve the world peace problem. And a lot of them saw Volapük as a method for doing that. That Volapük would allow us to experience de-Babelization, where we would break down the language barriers between countries, and maybe if we can communicate more effectively, maybe the coming war could be avoided. And so the Volapük movement took off all over the world, not just Europe, but everywhere. In cities all over the world, Volapük societies were being created. Books were being published about and in Volapük. New journals were being written in Volapük coming online every month. And it was reaching all classes of society. It wasn't just the intellectual elites learning this stuff. Everybody was interested in Volapük, and it was really taking off. And a lot of the success of the language was due to this guy. This is August Kirchhoffs. He was a Dutch linguist. And he wrote extensively about Volapük and traveled all over the world teaching the language. And he was so successful at doing that at the second Volapük conference, he was elected to be director of the Volapük Institute and given the job of popularizing Volapük throughout the world. The next year at the third Congress, at that Congress, they did all of the business in the Congress in Volapük. Even the waiters serving the meals were speaking Volapük. And Kirchhoffs at that meeting proposed a change to the language. There were some moods in the language which were rarely used, that were very complicated and difficult to teach and learn, and Kirchhoffs was proposing that they be removed from the language in order to make it more accessible to everybody. Basically, Volapük, the good parts. I love this guy. He was great. Schleyer was extremely upset about this. Schleyer insisted that the language belonged to him, and he demanded a veto over anything that the Congress might propose. At that point, the movement forked. About half of the attendees were in the German delegation, and they went with Schleyer. Everybody else went with Kirchhoffs. And then suddenly, chaos. You know, there are all these cunning linguists who said, well, as long as we're proposing changes, I got some ideas. And they started throwing new features out for what could go into Volapük. And other people saying, well, Esperanto's a better language, we should go with that one. And the thing collapsed. Almost overnight, Volapük was dead. So we don't know what would have happened had Volapük succeeded, but we do know what happened after Volapük failed. The world had its bloodiest century in history. So I told you, so they ended up with rebabblization. After it collapsed, they had more languages than when they started. And people continued to design languages. It's similar to the compulsion that causes some people to design programming languages. The guy who designed The Saint, you remember that TV show and the movie? He designed a language called Paleo Neo. The guy who designed the board game Careers designed a language called Interlingua. Maybe the most famous of all language designers was J.R.R. Tolkien, who designed languages for epic races like elves and dwarves, and wrote epic poetry in those languages, and then wrote histories to explain the context of those epics, and then used all of that as the backstory to The Lord of the Rings. He once gave a talk about his compulsion. He called it a secret vice. Anybody happen to know what the most popular invented language in the world is today?
Klingon?
Very good. It is Klingon. I told you that story because I want to introduce you to Kirchhoffs. Kirchhoffs was an amazing guy. After the Volapük thing exploded, things went really bad for him. His health suffered, and it went bad. But just before he got involved with them, he wrote the first book about modern cryptography. Prior to Kirchhoffs, cryptography was understood as the science of secret codes, generally codes written on pieces of paper. Kirchhoffs reinvented cryptography based on electronic communication, because they were now sending messages through the telegraph. And the properties of the telegraph are radically different than the properties of paper. And he worked this stuff out and came up with a set of principles which are still understood to be true today. He was one of these amazing thinkers who's just so smart and so far ahead of his time. So one of the things he wrote is called the Kirchhoffs principle. And he said, the design of a system should not require secrecy, and compromise of the system should not inconvenience the correspondence. So let me demonstrate what he's talking about here. So we have two correspondents, Alice and Bob, and they need to communicate, and they don't want to be observed while they're doing that. So they have a cryptographic system. In this cryptographic system, Alice takes her message, her plain text, and puts it in an encryption machine. She also puts a key into the encryption machine, and out comes a ciphertext. She then transmits the ciphertext to Bob, and it's entirely possible that that wire is being observed, and anybody can see it. Bob receives the ciphertext, he puts it in his decryption machine, which may be identical to Alice's encryption machine, and also puts in the same key, which they exchanged in a prior meeting, and that allows him to obtain the plaintext. And this is basically how all cryptographic systems work. The thing that Kirchhoff said, which was so amazing, was that there are no secrets in the encryption machine. The only secret in this system is the key. And I still see people today, academics who are saying we should try to keep as much of our system private as we can in order to frustrate the attackers. Kirchhoff said no. Just protect the keys. That's all you have to do. And he was right. And he was right because there is no security in obscurity. And it turns out the more secrets you have, the harder they are to keep. And just keeping the keys safe is really hard. So you should focus all of your attention on that. There's some people who take the Kirchhoff's principle so far as to say, we should publish everything about our system except our keys. And the good thing about that attitude is you're never confused about what are the important secrets in your system. So cryptography is not security, but the way that cryptographers think about problems is a really useful way of thinking, and we should think like that too. So I'm going to try to teach you to think like a cryptographer. I'm going to do that by teaching you about a cryptographic system called the one-time pad. This is the only cryptographic system which is guaranteed to be truly unbreakable. In all other cryptographic systems, if you have enough time and enough computer power, eventually you can brute force try every key and eventually you'll break the system. Not possible with this system. Guaranteed unbreakable, which is pretty nice. There are rumors that the hotline between the White House and the Kremlin is encrypted with the one-time pad. So this is how it works. We have a number of rules that we have to follow. The first one is that the key must always remain secret. This is true of every cryptographic system. Number two, the key must be at least as long as the plaintext. Now this is really unusual. In most cryptographic systems, the key is some fixed size, and the messages tend to be much longer than the key. This one says the key has to be at least as long as the message. Then the ciphertext is obtained by exclusive ORing the plaintext and the key. That is the algorithm. That is the implementation of the system. So it's really, really simple. So let me demonstrate it to you. This is my plaintext. This is the JSON logo. I'm using it because I can. Usually you think of a plaintext as being a text, but this is an array of ones and zeros, right? So we can encrypt that. This is my key. The key is the same size as the message. I'm going to exclusive OR them together, and if I do this correctly, you should not see any sign, any ghost, any whisper of the original message. If the message is completely obscured, hidden in the noise, then I have encrypted it correctly. The next rule says that the key must be perfectly random, or cryptographically random. Getting that kind of randomness is hard, and I went to a lot of trouble to get that into my key. So let me show you what happens if you don't. So this is a key. It looks just like the key I showed you first, except I made this one in Photoshop with a noise filter. Okay, and Photoshop's noise filters are not guaranteed to be cryptographically random. So if I exclusive OR my plaintext with this weak key, you can see it, right? It's leaking through. This is what cryptanalysts are looking for when they're breaking codes. They're looking for any kind of pattern, any kind of signal that's leaking through the noise. You are breaking an unbreakable code with your brain, and you're not even working hard at it. And the reason you're able to do that is your visual system is extremely effective at separating signal from noise. And that's what cryptanalysts do when they're trying to break a code. The next rule is so important, it is the name of the system. A key must never be used more than once. So the metaphor for how the system is used is, I will print two identical books of random numbers. I will keep one. I will give you the other one. When I want to encrypt a message to you, I will take the first sheet, I will tear it out, I will encrypt with it, I will then destroy it. When you receive the message, you will take the corresponding sheet out of your book, you will decrypt with it, and you will destroy it. You will never use it again. That's why it's called the one-time pad. So what happens if we violate that rule? So this is a picture of me. This was taken in Istanbul. I'm using it because I can. This you'll recognize is the first key that I showed you. This is the first good key. And I'm going to encrypt my picture with that. And again, it's completely hidden. I'm now going to exclusive OR this one with the first ciphertext that I obtained. And what happens is, because they each are exclusive ORed with the key will cancel out. And I'm left with the two messages exclusive ORed with each other. And there is no security in that. So cryptography is not security, but cryptography can teach us stuff about security. It's something I've found is that often we think incorrectly about how to use cryptography. If I'm looking at someone's system and there are obvious security vulnerabilities in them, and I point them out to the architect's first response is, we need to encrypt something. That turns out not to work. But thinking like cryptographers, that does work. And one of the tools that they use for thinking is they have a cast of characters who they use for reasoning about their systems. We've already met Alice and Bob. They are standard characters in the cryptographic show. But there are lots of other characters. For example, there's Eve. Eve is an eavesdropper. Eve might have a packet sniffer and is looking, Eve might be NSA, for example. Eve is looking at everything that's going between Alice and Bob. And Eve is hoping to accumulate enough stuff that eventually she'll have enough information to break their system, or at least be able to observe the pattern of their communication and do traffic analysis. Then there is Mallory. Mallory can do man-in-the-middle attacks. Mallory might be operating a public hotspot, and so Bob connects to Mallory's network thinking that he's going to connect to Alice, but he's actually connected to Mallory. Mallory connects to Alice, and Bob tries to log in. Mallory asks Bob, what's your password? Mallory connects to Alice. Alice says, what's your password? Mallory gives Bob's password to Alice. Mallory tells Alice, please transfer my funds. Mallory says to Alice, please change my password. Mallory says to Bob, sorry, we're down right now. Please come back later. Is that something we should be worried about? Yeah, we should be worried about that. Yeah. And then finally, in my own practice, I have a character I call Satan. Satan is totally malicious. He is very, very powerful. He is very, very smart. He is very, very determined. He's financed. He's got the tools. And he wants to hurt us and our customers. The approach that some people take to him is to say, well, we won't let him connect to us. You know, if you're Satan, you can't connect. That's called a blacklist, and that doesn't work. On the internet, it is so easy to create new identities that you can't do that, because he'll just be somebody else. So the other approach is, we will allow everybody to connect to us who is not Satan. That's a whitelist, and that doesn't work either in this case. The only thing that works is recognizing that Satan is going to connect to us, and he is going to do to us and our customers whatever we allow him to do to us and our customers. And so we have a responsibility to do everything right, so that the capabilities that we give to Satan are so limited and so weak that he cannot cause us harm. That is the only thing that works. Nothing else works. So because of that, security must be factored into every decision we make. Everything we do has security implications and can either make things better or worse for Satan. One big source of insecurity is the idea that we'll go back and make it secure later. It's very common that engineers who are building something will think the hard part is going to be to get the systems to boot, or the boxes to talk, or the pixels on the screen. Once we've done that, 2.0 will go back and add security. Turns out that doesn't work. Security is a really hard thing to retrofit. You need to get this stuff right at the beginning and all along, all the time. You can't add security just as you can't add reliability. These are things that have to be removed. That you have to remove insecurity, you have to remove unreliability. You can't add them. Having survived to this point does not guarantee future survival. Everybody who does business on the web has been under attack since the beginning of the web, and they have not destroyed us yet, but that does not guarantee that they won't. And so you have to always remain vigilant. The impossible is not possible, so don't expect impossible means to protect you. If a measure is not effective, it is ineffective, and we should not be wasting any time or attention on it. Don't attempt to prohibit what you can't prevent, and what you don't prevent, you allow. False security is worse than no security, because if you know you're not secure, you'll be cautious. And if you think you're secure and you're not, you will be reckless. So that brings us to the browser. So the browser platform is horribly insecure. We're still fixing it later after over 20 years. HTML5 made things worse instead of better by providing powerful new capabilities to the attacker without mitigating any of the pre-existing weaknesses. And yet, it is still the world's best application delivery system. It is better than everything else, including systems that were designed after the web. Everybody refused to learn the web's lessons. So one of the things that the web got right, that virtually every other platform has gotten wrong, is the web does not have a blame the victim security model. A very common thing in systems is that if a system has to make a decision about security and does not have enough information to make a correct decision, it will ask the user. And it will ask the user in language that the user cannot understand. And if the user says no, then it fails. And if the user says yes, it is the user's fault for giving up their security. This is not a valid model of security, but we see it all the time. For example, I recently bought an alarm clock at the Android store. And it was only after I bought it that I looked at the permissions, and one of the permissions it wanted was unlimited access to the internet. Okay, wait a minute, why does a clock need unlimited access to the internet? And my choices are now to let my clock leak everything it can find in my device and send it who knows where, or I'm out the money I spent on the clock. I mean, that's not a good model of security. So the thing that the browser got right, that everything else got wrong, was the answer to this question. Whose interest does the program represent? From the beginning of computing, it has always been assumed that a program represents the owner of the machine, or at least the owner of the account. And the browser says no, the program represents a site, and a site does not necessarily represent the user, which was absolutely right, and nobody else has figured that out. Unfortunately, the web got a lot of other things wrong. The web didn't anticipate that there could be more interests involved in a page than just the user and the site, and that a malicious party can exploit coding conventions to inject malicious code. And that malicious code gets all of the rights of the site. This is known as the XSS problem. We'll talk more about XSS in a minute. But to ground this, I mean, you're always hearing people whining about security and how terrible all the problems are. Let's get really specific. In this XSS attack, what can actually go wrong? What can an attacker do if he can get some script onto your page? The attacker can request additional scripts from any server in the world. Once it gets a foothold, and it only needs about that much text in order to do that, it can then obtain all of the scripts it wants. Browsers have a security policy called the same origin policy, which limit the ability of the browser to get data from other servers, but there is no limit at all on how much program you can load from the most evil server in the world. An attacker can read the document. The attacker can see everything the user can see, and even things the user can't see. The attacker can see comments and hidden fields, cookies, everything we transmit to the browser, the attacker gets access to. The attacker can make requests of your server, and your server cannot detect that the request did not originate with your application. If you're using SSL, and you should, the attacker gets access to your secure connection. If your server accepts SQL queries, then the attacker gets access to your database. Now, if instead your server is constructing SQL queries based on information that it gets from the browser, then you're only probably giving access to the attacker to your database. And that's because SQL was optimized for SQL injection attacks. Thank you. An attacker has control over the display and can request information from the user, and the user cannot detect that the request did not originate with your application. So modern browsers have anti-phishing Chrome. And unfortunately, most users don't pay any attention to that. But if they are paying attention to it, in this case, the browser is saying it's good, because all the browser is concerned with is where did the HTML come from. The browser doesn't pay any attention to where did the script come from. And the script could have come from anywhere, and the script is what's going to cause the damage, not the HTML. So knowing this, on some sites, whenever something dangerous is about to happen, they will ask the user to type their password again. And the theory is that only the user will know the password. And that way we can be confident that this is not going on. Except that the attacker has control of the display. And so the attacker can ask the user, what's your password? And the browser is saying, good, tell him. So if you're operating one of these sites which asks people to re-identify themselves at unlikely times, what you're actually doing is training your users to give up their passwords the instant the attacker gets control. Then the attacker can send information to servers anywhere in the world. Everything that they learned by scraping the page, by talking to the user, by querying your database, they can then send this to the most evil server on the planet. Again, the browser has a same origin policy which limits their ability to receive data from other servers, but it puts no limit on their ability to send all of this stolen information. So in the browser, is this starting to freak anybody out? Just why are we doing business on this platform? Is that anyone?
Well, I thought that I just kind of walked through the world going, well, Chorus takes care of all this for us, right? But
No, nobody's taking it.
I'm really waiting for you to explain to me. I don't know. I want to know what I'm doing wrong.
I think I'm making it clear. Anyway, the browser does not prevent any of these. Web standards require these weaknesses. If you were to build a new web browser from scratch, if it didn't subject you and your customers to all of these potential problems, it would not be standards compliant. And the consequences of a successful attack are horrible. There's harm to customers, there's loss of trust, there are legal liabilities. There's even talk now about criminal liabilities for negligence for allowing people to have their identity stolen. So this attack, which I just outlined, is called the XSS attack, which stands for cross-site scripting. Now, it should be called CSS, but there was another abomination called CSS, so they call it XSS. But the name is a problem. The name says that there's something wrong with cross-site scripting, but in fact, that is a highly desirable thing. We want to be able to have sites cooperate with each other, and businesses and services cooperate with each other, which might be located on different sites. That's a desirable thing. It's not a bad thing. And there are forms of this attack which do not require the use of a second site. So the name is just completely wrong. That the security experts who first identified this attack did not understand what this attack was. They gave it an incorrect name, but the security industry is still operating on that name. And they're expecting you as practitioners to understand what they're meaning when their language is incorrect. Cross-site scripting attacks were invented in 1995 when JavaScript was first released, and they've been going on ever since. We're just now on the 20th anniversary of cross-site scripting attacks. So we have made some baby steps. For example, there's a content security policy thing that's in browsers now. It took a long time to get it out, but it's out there. Unfortunately, most sites aren't using it, so it's still unsafe by default. In fact, in order to use it, it means that a lot of common practices now become illegal, as they should, but because they're common practices, it's not going to get used. A mashup is a self-inflicted XSS attack. And it turns out advertising is a mashup. And the most reliable, cost-effective method to inject evil code is to buy an ad. So why is there XSS? So when things go wrong at an architectural level, it's never just one thing. You need a lot of things to go wrong simultaneously, and that happened on the web. The first one is that the web stack is too complicated. There are too many languages, each with its own encoding, quoting, commenting, and escapement conventions that can all be nested inside of each other. I've called this the turducken problem. It's very difficult to look at a piece of code and determine that it's going to be benign in all contexts. That's a very hard analysis to do. And it's made even worse because browsers do heroic things to try to make sense out of malformed content. In fact, HTML5 began as an attempt to standardize the terrible, stupid things that browsers do to try to make sense of invalid HTML. Then that's compounded with the popularity of template-based web frameworks that are optimized for XSS injection. I hate templating. We'll talk more about those later. And then finally, the JavaScript global object gives every scrap of script the same powerful capabilities. And yet, as bad as it is at security, the browser is still a vast improvement over everything else. So the problem is not a cross-site scripting attack. It is a confusion of interests. The browser distinguishes between the interests of the user and of the site, but it did not anticipate that there might be other interests involved, and that's where it fails. So within a page, interests are confused. So an ad, a widget, an AJAX library, an analytics library, anything that gets loaded from a third party, all of that code gets exactly the same rights as you do. It means you are trusting everybody in all of those other institutions. Now, JavaScript gets close to getting it right, and I think JavaScript can be repaired and become an object capability language. We'll talk more about what that means. HTML, I don't have any hope that we're ever going to fix HTML, and the DOM, which is that hideous API that HTML uses, is horribly insecure. I don't see that going away either. So this stuff is not going to get fixed in a hurry. So it's up to web developers to create secure applications on an insecure platform. And that is really, really hard. It shouldn't have to be that hard, but it is that hard. But there is hope in the principle of least authority, which teaches that any unit of software should be given just the capabilities it needs to do its work and no more. Capabilities can be seen in the actor model, which was discovered at MIT in 1973. The investigation of the actor model led to the invention of Scheme, which led to higher order functions and all that good stuff, and also led to actors. So in the actor model, an actor is a computational entity. It's like asynchronous object systems. An actor can send a message to another actor only if it knows its address. An actor can create a new actor, and an actor can create messages. Web workers are kind of like actors. Web services aren't, but should. There was a system called Waterkin that was developed at HP Labs, which applies the actor model to web services. I think this stuff is brilliant. It gives you very reliable systems. I highly recommend getting into that. So one of the things that comes out of the actor model is the idea of capabilities. So an address to an actor is a capability, or a reference to an object is a capability. So let's apply capabilities to object-oriented programming, looking at object capabilities. So here is an object. A is an object. It has state and behavior. Object A has a reference to object B, because objects can have references. Object A can communicate with object B because it has that reference. Object B provides an interface that constrains access to its own state and references. So object A does not get access to B's internals, only to its interface. This is why I like freezing in JavaScript, because in JavaScript that is the only way to guarantee this. The only way to make good, reliable objects. Object A does not have a reference to C, so A cannot communicate with C. It's as though there is a firewall between A and C, except that firewall is implemented at zero cost. An object capability system is produced by constraining the ways that references are obtained. A reference cannot be obtained simply by knowing the name of a global variable or a public class. And in fact, there are exactly 3 ways to obtain a reference: by creation, by construction, and by introduction. By creation means that if a function creates an object, it gets a reference to that object. By construction means that an object may be endowed by its constructor with references. This can include references in the constructor's context and inherited references. And then 3, this is the interesting one, by introduction. So here, A has references to B and C. B and C have no references, so they cannot communicate. But A wants them to be able to communicate. So A communicates with B, passing a reference to C. And once that is done, B has now acquired the capability to communicate with C. That's why this is called the capability model. If references can only be obtained by creation, construction, or introduction, then you may have a safe system. And if they can be obtained in any other way, you don't. So potential weaknesses to watch out for include arrogation, corruption, confusion, and collusion. Arrogation means to take or claim for oneself without right. This includes global variables, public static variables, standard libraries that grant powerful capabilities, address generation, which is why C++ can never be a secure language, and known URLs in web systems. Corruption. It should not be possible to tamper with or circumvent the system or other objects. Again, that's why freezing is so critically important. Number 3, confusion. It should be possible to create objects that are not subject to confusion, because a confused object can be tricked into misusing its capabilities. And then finally, collusion. It must not be possible for 2 objects to communicate until they are introduced. If 2 independent objects can collude, they might be able to pool their capabilities to cause harm. Some capabilities are too dangerous to give to guest code, so we can instead give those capabilities to intermediate objects that will constrain their power. For example, an intermediate object for a file system might limit access to a particular device or directory or so on. Ultimately, every object should be given exactly the capabilities it needs to do its work and no more. So capabilities should be granted on a need-to-do basis, just as we grant information on a need-to-know basis. The principles of information hiding, which we know leads to good designs in software systems, are enhanced when you're thinking about capability hiding. Intermediate objects or facets can be very lightweight, and class-free languages can be especially effective. I've tried making facets in Java, and it turns out it's really hard, because every time you want to make a little connector, you have to make another class, and that's a lot of work. Whereas in JavaScript, most of these things are just a simple object or a generator, and boom, you're done. So here the facet object limits the guest object's access to a powerful object. The guest object cannot tamper with the facet to get a direct reference to the dangerous object. References are not revocable in a capability system. Once you introduce an object, you can't ask it to forget it. You can ask, but you cannot depend on the request being honored. So here the guest object has a reference to an agency object. The guest asks for an introduction to the powerful object. But the agency instead makes a facet and gives the facet to the guest. And the facet might be a simple pass-through. The guest can then call the facet will then call the powerful object. When the agency wants to revoke the capability, it tells the facet to forget its capability. The facet is now useless to the guest. This is what you did yesterday. Yesterday's revocable function was this pattern. So you know these things are really easy to implement. A facet can mark requests so that the powerful object can know where they came from. That gives us accountability. Facets are very expressive, they're easy to construct, they're lightweight, they provide attenuation or power reduction, they give us revocation, notification, delegation, and it turns out the best object-oriented patterns are also capabilities patterns. Sometimes when you're trying to design a system and you're trying to figure out, does this capability go there or there? And sorting those early on in the, when you're doing the design and taxonomy is hard. But if you think about it in terms of capabilities, what is the least amount of power I need to give to this guy in order to have it work correctly? You tend to end up with the correct designs. That thinking about security makes system designing easier, not harder. So facets can reduce the power of dangerous objects. Most code should not be given direct access to dangerous things, for example, in the browser, inner HTML or document.write. Instead of trying to guess if a piece of code can do something bad, we can give it a safe set of capabilities instead. You know that even if it is bad, it's limited in what it can do. And capabilities can aid in API design. So one of the nice things about this model is it completely changes the economics of hacking. In most architectures, if you can confuse an object, basically that gives you access to everything in the system. Whereas in this model, if you can confuse an object, you get the capabilities of that object, but only that. And in most cases,
you can confuse an object?
Well, yeah, the object is not created correctly, and you can cause it to do something that it's not supposed to do.
Okay.
You might be able to get control of what that object can do, but you don't get control of everything that the system can do. So we change the economics of hacking. There's a really nice talk on YouTube about this stuff, The Lazy Programmer's Guide to Secure Computing by Mark Stiegler. Stiegler's premise is that the best programmers are lazy, but they're lazy in a way which avoids future work. And if you take that approach, that you tend to lead yourself to secure systems as well. So this morning we did this exercise, right, where we found this leakage because of the unexpected thing that this does, which compromised our security. So we need to understand for this stuff. We need to plan for it. We need to improve the language. We need to improve our understanding of the language so that we're not compromised by it. That attack is an example of a confusion attack. And that's why I hate confusion so much, because confusion is what causes our systems to fail. Confusion aids the enemy. Bugs are a manifestation of confusion, but also security exploits are a manifestation of confusion. And usually attackers get to take over our systems when their understanding of our systems are better than ours. And unfortunately, that tends to happen a lot. And the way we stop that is by getting a better understanding of our own systems, and we do that by eliminating as many sources of confusion as possible. I have no tolerance for confusion. I want to eliminate as much confusion as I can.
So a confusion attack is when you don't know how you don't understand how the code that you're writing works.
We think the system works in a particular way. Yeah. And the attacker, by studying us, figures out that's not how we work. And he's able to exploit that. In fact, virtually all security exploits are like that. That we never intentionally go public and into production with code that we know has security vulnerabilities in it, and yet everything that's ever been deployed has security vulnerabilities in it. And it's because we're confused about how our own systems work. We need to stop doing that. So with great complexity comes great confusion. So that's why I'm a minimalist. I want to find the simplest solution in all cases, because those are the things that are easiest to reason about. So we should keep everything as simple as we can. We should keep our code bases as clean as we can. If we allow our code bases to get crufty, then they become harder to understand, more likely to be confusing, and will get exploited. So we should always code well. Good code is ultimately cheaper to produce than bad code, so we should always make good code. Good code is easier to reason about. Code that is difficult to reason about is more likely to be problematic, and we should have strict conformance to good style rules. which means that if we're writing in JavaScript, everything should pass JSLint without exceptions. We should not put anything out on the web which is not at least that good. You should never trust a machine that is not under your absolute control, and then not even sure about all of those. But one thing for sure, you must never trust the browser. It cannot and will not protect your interests. You need to properly filter and validate all input that you get from the browser. You need to properly encode everything that you send to the browser. The context of that encoding and decoding and filtering is critical. You need to filter and encode for the correct context. So let me tell you what I mean about trusting the browser. So this is a true story. A few years ago, a friend of mine was going to go visit China. So he bought a ticket on a famous airline. And it's an expensive flight, so he bought a coach ticket. And then he realized, wow, it's a really long flight. It's really uncomfortable. It would be much nicer to upgrade to first class. So he went to the website of the airline and looked to see if upgrades were available. And they were, but you needed a certain number of upgrade certificates. And it told him his number was 0 because he doesn't fly all that often. So he was very disappointed until he opened the debugger. He found the variable that contained his number of certificates, and he flew first class to China. It's a true story. The reason that worked was the guys who designed that system assumed that there is a certain URL that could only be generated if a certain set of conditions were true. And they were relying on the browser to guarantee that. And the browser will not guarantee that. You cannot trust the browser. Another browser story. In the first days of e-commerce, when online stores first started happening, they didn't understand yet how to scale web systems, right? They tried to do all of the work on one server, and very quickly they got an amount of traffic was bigger than one box could handle, and they were panicked. About the same time, JavaScript comes online. And they go, great, we can now offload all this processing onto the browser. So they now have the browser do all the work of preparing the invoice and totaling everything up. They just allow the browser to then submit this thing, which then gets sent directly to fulfillment. So if you can figure out how to type a URL, you could order anything you want and pay whatever you think is reasonable. So it turns out there are good reasons to do stuff in the browser. Most of them are to provide a better user experience. So you can avoid the thing where the user fills in a form and then you kick it back in their teeth because they got something wrong. We can help them do that and make it pleasant. But that doesn't mean that the server shouldn't check every detail of it and make sure that it happened right. You have to do that. So templating is this process. We'll talk more about templating this afternoon. I hate templating. Because templating, the browser is a gun pointed at your head, and templating is what pulls the trigger. This is the simplest XSS attack, just to show you what the beast actually looks like. So in this attack, the attacker tricks your user into clicking on a URL that looks like that. It's a really weird-looking URL with angle brackets and crazy stuff in it. And you might think, no user would ever click on that. And unfortunately, no, they will. And if they're smart enough not to click on a URL that looks like that, they'll probably click on a bit.ly URL, or they'll probably accept a QR code. So yeah, they're going to go there. And so it used to be that web servers by default would simply take the file name and stick it in the body of a 404 page and send it back. And in this case, now in an HTML context, that becomes a script tag, which will then execute and load script from the world's most dangerous server. And they get access to everything that you've got on the browser. They got your cookies, they got your local storage, they've got the Chrome saying this is a valid thing, so when they ask for your password, everything's good. And there are thousands, maybe millions of variations on this. And a security expert can get some fame by discovering another one. And they can always do that because there is an endless supply of these things. But the solution to all of these is exactly the same. everything has to be filtered correctly, everything has to be encoded correctly. So if you encode this and turn those into entities before putting it on, then it becomes inert. And it becomes really important to do that everywhere. And if you do that correctly everywhere, then these sorts of injection attacks cannot happen.
I didn't get the first, I think I'm missing the first part of this. So you go to yoursite.com/ all this nonsense with the script that's in there.
Yeah.
And the server responds with 404, and it sticks that content in it.
Yeah, it takes the file name, and puts it in, says this is the file we couldn't find.
Oh, I see. So, okay. And now this script runs a form that says, please, submit your password, and they submit their password.
Yep.
Whatever it is.
Whatever it is.
In fact, the script can now talk to both sites.
Yep.
And you're saying the mitigation is done in the 404 page you have on your server?
Right. So, in fact, every page your server can construct needs to do this encoding correctly for all cases, for all inputs.
You should never tell them what they submitted. It should just say that page isn't found.
Right. Like another example, this is one that doesn't require a second site. On Yahoo, they used to have profile pages. And on your profile page, there's a box for gender. And being very nice people, they allowed you to type anything you wanted into that box. So it wasn't like you have to pick M or F. They said, whatever you want, that's okay. And there were a lot of people who figured out, oh, it starts with an angle bracket, and it's type a script tag in there. And so it means every time anybody looked at your profile page, they can steal your account. There was a similar thing that happened in MySpace. There was a guy named Sammy who figured out, MySpace at that time was a little bit smarter and had some filters, but this guy named Sammy figured out how to get around them. And so he injected a script that whenever anybody looked at his profile page, the script would run and then add him to their heroes list, which is the best spot on a friends list, and put that script onto their page as well. And so the number of people who had looked at one of these pages doubled every minute. Or no, every hour. So in 20 hours, he had control of 2 million accounts. And about that time, MySpace went, whoa, what's going on? And they shut it down. But you can still search out on the web for Sammy is my hero, and you'll probably still find some of these out there. So that's a version of this attack. And Sammy turns out to be a nice guy. Or I don't know if he's a nice guy, but he recognized, whoops, I didn't expect I'd take over 2 million accounts in a day. So he turned himself in and was charged with a crime and
Probably got a sweet job working somewhere as a white guy.
I'm sure Sammy did okay, but he could have been a bad guy, right? He could have just kept it to himself and figured out how to exploit these 2 million people. So you also need to worry about concatenation. So the plus sign operator in JavaScript is dangerous, depending on how you're using it, because you can be taking bits of string and putting them together. And in some cases, if you're just putting together text, it's not a problem. But if you're doing something like assembling JSON or assembling HTML, there's a potential for that to go bad. So whenever possible, you should be using good encoders and writers and not just trying to plus things together. So I'm very happy to report that this is no longer apparently a source of insecurity. A manager, when being warned that we need to protect against this, would ask, why would anybody do that?
Oh no.
We now know why they'll do
We still
that.
hear that.
Do you
From
really?
managers.
Oh, well, that's a problem.
Yeah.
Yeah. We now know why they will do that. They will do that because we didn't prevent them from doing that. In the case of some companies, those companies will unintentionally pay them to do that. In some cases, maybe pay them really well to do that. So these are things which are not security, which are sometimes thought of as being security. For example, inconvenience. We can't stop them, but we can slow them down. we'll put speed bumps on the information superhighway. We'll stop them. That doesn't work. Those things tend to inconvenience you more than them. It's just, again, if it's not effective, it's not effective, and don't waste time on it. Identity is not security. That finding out who someone is doesn't answer the question of what should they be allowed to do to you. Tainting is sometimes cited as a model of security that doesn't work. It's a model where you try to track the source of data and how it's transformed over time, and try to determine at what point it becomes tainted or corrupted, but it doesn't work. And then finally, intrusion detection is not security. There are some system administrators who are so tired of being hacked and they've given up all hope of stopping it. They just want to know when it's happening, but that's not security. The biggest avoidable source of security, and we'll end here, is mismanagement. It's when a manager says, we're going to get this past the security guys because we got a deadline, we got to meet it, we got to get out there, I got a bonus on the line, we're going to go. Don't let that happen. You got to kick it up, because no company can afford to have this kind of stuff going on in their sites for any possible short-term gain. It's time now for asynchronicity. So there are two kinds of functions in the world. There are synchronous functions and asynchronous functions. So let's first look at synchronous functions. A synchronous function is a function that does not return until the work is completed or has failed. So all of the functions that we wrote over the last couple of days have been synchronous functions because that's how they worked. And that's a very useful thing to have in a function, because it means it's easy to reason about its behavior over time. That when a synchronous function calls another synchronous function, the caller is suspended in time and nothing advances until the callee returns. If the caller is looking at a clock at the moment that they make the call, their experience will be that the hands jump forward quickly, but otherwise they're not aware that this stuff has happened, except that the thing that they asked for has magically been completed. And that makes it easy for us to reason about things unless we need to make multiple things happen at the same time. You can't make multiple things happen at the same time if you're suspended in time. So the way that's often mitigated is by use of threads. A thread allows to have multiple threads of execution happening through a memory space at the same time, so that lots of things can happen at the same time. Unfortunately, races come with some problems, threads come with problems, including races, deadlocks, and other reliability problems and performance problems, and we'll look more at these. So the threading model, like all models, comes with pros and cons. And the first pro is a really important, a really significant one. No rethinking is necessary. You can take any existing piece of code, put it in a thread, and it'll just work that way. You don't have to make any changes to it in order to introduce it to a threaded environment. Now, that doesn't necessarily mean that you'll never need to change it, but the starting up phase is really easy. The next pro is that blocking programs are okay. It's okay for programs to block. And in fact, that is what threads are for. Threads exist so that things can stop and have other things happening while it's stopped. So execution will continue as long as any thread is not blocked. But there are some cons. The first con is that there is stack memory allocated per thread. This used to be a significant problem. It's not anymore. Moore's law has continued to ramp on memory capacity, and so thread stacks are now in the noise. We don't care about them anymore. A more important con is that if two threads use the same memory at the same time, a race may occur. And in fact, this is a big problem. So a lot of people have been asking, when are we going to get threads in JavaScript? And the answer is never. And let me illustrate why. So here we have two programs which will each run in its own thread, and we will run them possibly at the same time. And there are a number of possible consequences of this program. One is an array containing A and B, and the other is an array containing B and A. Because we can't control in what order these two threads run, these are two possible outcomes. But that's not the race I'm worried about. The race I'm worried about is this one. Another possible outcome of this program is an array containing only A, or an array containing only B. And this is not due to anything except what's happening in these two statements. And you can look at these for a long time and try to figure out, where did half of my data go? You know, how did this fail? It's really hard to reason about programs that race in threads. So let's zoom in on this and look at what's going on. So that's the first statement. One of the things that makes JavaScript an expressively powerful language is that one statement can do the work of many statements, and that's the case in this one. That one statement on the top does what the 4 green lines do. It'll get the current length, it will assign to that part of the array. If the length of the array has increased, then we'll make that change. And if we look at the second thread, it also expands into stuff like that. And we cannot control how these might be ordered in actual execution. So one possible ordering could be both capture the length at the same time. And both will be using that to store into the array, and both will be using it to change the length of the array. And as a result, whichever one runs second is probably going to win. So that's where half of our data went. And this stuff is really hard to reason about. For one thing, you can't see it in the original code, but it's worse than this because each of these statements could expand into multiple machine language statements, and you don't know how those are going to interleave. And each of those could expand at the low level into micro instructions, and you can't control how those will interleave. And it may be that the real-time behavior of this threaded code changes according to loading. So it might be working fine during development, but then fail when we put it in production, or it's working fine most of the year, but it fails at Christmas. You know, as things change, things that wouldn't appear to affect the behavior of the program can actually radically affect the behavior of the program. So the way we mitigate this stuff, so it's impossible to have application integrity when we're subject to race conditions. So we mitigate that with mutual exclusion. Mutual exclusion allows only one thread to be running in a critical section of memory at a time. And there's a long history of this stuff, starting with Dijkstra's semaphores and Hoare's monitors, the Ada rendezvous, and now we call it synchronization, but these are all transforms on the same idea. This used to be operating system stuff. It used to be only operating systems were concerned with mutual exclusion and running multiple things at the same time. But this has all leaked into applications because of networking and because of the multi-core problem. The concern with networking is that we want to be able to have stuff happening while slow things are happening. And one of the slowest things we can do is go out to the network, because that has large latencies and in some cases unknowable latencies. And so you can be stopped for a long time, and generally you can't afford to have systems be suspended for that long. So you need threads in order to allow them to continue. Then there's the multi-core problem. CPU designers have lost the ability to make CPUs go faster. So instead, they're giving us more of them. And we don't know how to use them. Unless, if you have a problem that's embarrassingly parallel, then we can take advantage of it. But most of what we do is embarrassingly serial. And we don't know how to take multiple cores and put them in our applications and get a significant benefit from it. So that's where we are. So with mutual exclusion, only one thread can be executing in a critical section at a time, and all other threads waiting to execute in the critical section will be blocked. If the threads don't interact, then the programs can run at full speed across all the cores. But if they do interact, then races will occur unless mutual exclusion is employed. Unfortunately, mutual exclusion comes with its own dark side, and that is deadlock. Here we have two threads, Alphonse and Gaston. They are both programmed to wait for the other to stand up before they can stand up. This is deadlock. It turns out computer systems do this all the time. Here's another example. This is a real-world example from Sao Paulo. You can think of, apparently they do this all the time. You can think of each of these cars as being a thread which is ready to run. It's just waiting for the thread that's blocking it to get out of the way. So deadlock, that's a serious thing. So an alternative to all of that are asynchronous functions. Asynchronous functions return immediately. You call it, it comes right back. There's almost no passage of time. And success or failure will be determined somehow in the future. When the asynchronous function returns, there is no solution yet. The solution might happen maybe later, but not now. So we like to use asynchronous functions in turn systems. A turn is started by an external event, such as delivery of a message or completion of an asynchronous request, a user action, or the ticking of the clock. Then a callback function associated with that event is called, and it runs to completion. It doesn't have to worry about races because nothing else will get to run until it's finished. When it returns, the turn ends. So there's no need for threads, no races, no deadlocks. It's a very reliable, very straightforward programming model. We call it turns because of games. It comes from chess, that in chess, when it's my turn, I get to control a piece. You don't get to touch any pieces until my turn is done, and then it exchanges. We're doing a similar thing with functions and events. But when you're using turns, it requires that you have to follow the iron law of turns, which says you must never block, you must never wait, you must finish fast. If you have any code which has to block or has to wait or can't finish quickly, it has to be isolated and run in a separate process. It is not allowed to run in the turn system. So that's a cost, right? I mean, you're allowed to run some code, but there's some code which you're definitely not allowed to run. We usually do this in an event loop. Event loops are turn-based systems, and they come with pros and cons. The pro is a huge pro. It is completely free of races and deadlocks, and that's a huge advantage. Any system that, applications should never be written, I think, in systems that use threads because it's just too hard to reason about them, and it's too unreliable. Another pro is that there is only one stack, and we reuse that stack on every turn, so it's extremely memory efficient, which is of no interest at all. Again, because memory is so cheap, the fact that we're memory efficient is irrelevant. What's more important is that it is very low overhead, because all we're doing in the event loop is take something off an event queue, hand it to a function, let it run, take the next one, and so on. So there's very little overhead. Whereas in a threaded system, you're doing lots of locking, you're doing lots of process switching and context switching, which are the most expensive things that CPUs know how to do. In a turn-based system, you're not doing that. You're just pulling something off a queue and running it, pulling it and running it. It's also a surprisingly resilient programming model. If a turn fails, it's usually the case that the program can still go on. For example, if you ever take any web browser and open up the debugger and just go wading out into the web, you're going to see almost a constant string of failures. It's amazing how much failure is going on in web pages all the time. But if you don't have a debugger open, you don't see it. Now, in a threaded environment, when something fails, then there'll be an exception. One of the stacks in one of the threads will get unwound, and it'll try to recover. But that thread may now be in an inconsistent state compared to the other threads because it's lost all of this context. And so that could lead to cascading thread failures. And so it tends to be a fairly brittle model. Whereas what we see in web browsers is as long as there's any button that still works and the user can find it, there's a good chance they're going to be able to complete the transaction and never know that the thing has been failing hugely behind the scenes. Now, there are some important cons here. The most important con is that programs must never block and that turns must finish quickly, that we have to obey the law of turns. That is definitely a con, but it's something that has to be respected. Also, another con is that programs are written inside out, and that makes some people cry. They call it's inversion of control, it's unnatural, it's an unrealistic way to write programs, we can't do it, it's too hard. Wah, wah. But actually it turns out it's not hard, it's actually pretty easy. So we do things in event-driven systems. They're turn-based. There's no preemption, which is really good. That makes them very reliable. We associate events with actions. And it turns out, despite the people who are complaining that it's very hard and inside out and unnatural, it's actually very easy. And in fact, beginners can do it. It's actually very hard. And in fact, it's how all user interfaces are implemented, even on systems that have threading, because it just turns out this is the best way to implement a user interface. Threading has or event loops and asynchronous programming has a long history. It was done in real-time systems and experimental systems and game systems for a long time. It doesn't get into the mainstream until the Macintosh. Macintosh is the first consumer device, although it's kind of expensive for a consumer device, which is programmable only in a turn-based manner. Prior to that, everything has been using blocking I/O going all the way back to Fortran. And our memory of this is that when Apple introduced, and Steve Jobs introduced the Macintosh in 1984, it changed the world and turned Apple into one of the world's most successful companies. And that's not actually what happened. This machine came very close to bankrupting Apple. And part of the reason was that they couldn't sell very many, and the reason for that was that they couldn't convince programmers to write programs for this machine, because they had never seen an event loop before and didn't understand how to write programs in that model, and they were complaining it's unnatural, it's too hard, it's inside out, wah, we're not going to do it. Instead, they wrote for MS-DOS, which was horrible and crappy, one of the worst things ever imagined, which outsold this by several orders. It was just ridiculous. So the thing that changed this, which turned this machine into a success, was HyperCard. HyperCard was a system that was built by Bill Atkinson. Bill Atkinson had written QuickDraw, which was the graphics layer of the original Macintosh. He also wrote the first paint program called Mac Paint. It's hard today to recognize it as a paint program because it only had two colors, black and white. But it came free with the machine, and when you bought a Macintosh, that was literally all there was to do with it. And so people did a lot of stuff with Mac Paint and called it art. His next program was HyperCard. He took Mac Paint and allowed it to work on several pictures at the same time, only one of which would be visible. He called these pictures cards, and that a file was a stack of cards, or a stack. And then he got the idea that he could put buttons on the cards and wire those buttons to behavior and put fields on those cards and allow those fields to contain text, which he could then search for and process on. And then he added an event-driven programming language to that called HyperTalk, which was an event-driven programming language. Everything in it was events, and you would say things like on key up and on mouse down and so on. And beginners loved HyperCard. They got all into HyperCard. They were writing stuff. They'd start with very simple little event handlers and then start doing stuff that was much more sophisticated, inventing whole new classes of applications that all ran into HyperCard. There were predictions that HyperCard was going to be the future of software development, and it might have had Apple not run it into the ground. When Atkinson originally demanded of Steve Jobs that it be distributed for free with Macintoshes, and Jobs agreed, and that's how they did it for several years. Once they saw how successful it was, they decided we need to figure out how to monetize this. And in the process of doing that, they killed it to death. But it worked, and it inspired stuff that happened in the browser. In fact, you see that home thing, the concept of the home page came out of HyperCard. That's where the stuff came from. And because the beginners were writing in HyperCard, we know it's easy for beginners to use event-based systems and to do asynchronous programming. JavaScript is now moving to the server. After having conquered the browser, it's now moving to the server, and it's conquering there too. Which is great because it means all of the skill that we've developed in doing stuff on the browser side, we can now bring those skills back to the server side. It means you only need to be really competent in one language, and that can help save some time. Unfortunately, what servers do is quite different than what browsers do. In fact, it's so different that you need a fairly different programming model. So we're doing server stuff now in Node. Node implements a web server in a JavaScript event loop. It's just a high-performance event pump. It's very efficient, very fast, can do a tremendous amount of work. It does file I/O correctly for the first time. Going all the way back to Fortran and COBOL, file I/O has always been blocking. And in Node, we finally get non-blocking file I/O. So we do it asynchronously. So when you want to read a file, you pass in a file name and a callback function. And when the file is read, it'll call your callback function and you get the data, and it's great. And so the programs don't block on doing file I/O, because blocking would violate the law of turns, and we never violate the law of turns. So in Node, everything is or can be, should be non-blocking. Unfortunately, like everything that has anything to do with JavaScript, Node doesn't get everything right. And a couple of things that I'm really unhappy about with Node is that Node has a number of synchronous functions baked into the API. And these synchronous functions block everything. And so you go from having a very fast, high-performance system to a very slow, low-performance system instantly because you're blocking. Nothing else gets to happen until the synchronous calls are done. So I would like to outlaw those synchronous functions. Unfortunately, what we've seen in the JavaScript community is if you put something really stupid into an API, there are web developers who say, I have a right to use it. And there are these synchronous functions in Node which should never be used. But because they're in Node, there are people using them, and they violate the law of turns. Then I don't like the requires thing, because it is also blocking. The very first version of it on Node was asynchronous, which is the correct way to do it. And there were complaints that, oh, it's too hard, it's inside out, and we only start things up in the morning when we turn the servers on, and so once they get warmed up, then it doesn't matter. Except that's not true. I mean, we're bringing servers up and down all the time, so anything which blocks is a bad thing. So fortunately in ES6 we're getting a new module system which obsoletes that, so that'll be better. But what we're doing, servers are significantly different than browsers. So in a server, we're not dealing with events, we're dealing with messages. Message comes in from the network, we'll do something, we'll send another message out. It's all about messaging. A Node server is actor-like in that it's a thing which receives messages and sends messages. But the simple event model that we use on the browser doesn't really fit the workflows that we do on a server. For example, we may have things which take several sequential steps. Like a request comes in, we take that request, we have to send something to a database, get something back. We take that information, we use that to go to another database and get stuff back. So each of these things depends on the previous thing. How do you do that? If you don't know how to do it, the naive approach is to write deeply nested event handlers. So in the event handler of one thing, you make the request of the next service, and in its event handler, you make the request of the next one, and that leads to code which is extremely brittle, extremely hard to maintain, low performance, it's all bad stuff. Then we have the opportunity to do things in parallel. It might be a request comes in, and we can go to several systems at the same time because the requests are not dependent on each other. So they're independent requests, and by going in parallel, we get to change the performance of the thing significantly, because instead of waiting for each to finish sequentially, instead of taking that much time, we only have to wait for the slowest of those things, which is usually a much shorter time. So we can significantly improve our response processing. Unfortunately, each of these requests may be coming back at unexpected times in unexpected orders. And how do you deal with that? And some might not come back at all. How do you deal with that? And so that's hard. So if you don't know how to manage that, the naive thing is to not do it in parallel, instead do it sequentially with deeply nested event handlers, which is, again, quite awful. Then in addition to that, you may have to deal with limited time. You may have SLAs or other policies which say, we have to get a response within so many milliseconds, and if we don't, we have to go to plan B. We can't just keep the request hanging for some amount of time. And then we have to deal with cancellation. If we go to plan B, we want to stop all of the work which is no longer necessary. How do you do all of those things in deeply nested event handlers? Functional programming to the rescue. So one of the reasons why after 40 years functional programming has suddenly become important is because it contains the solutions to these problems. And we've got a lot of history with this stuff. And going back to futures, which came out of Dataflow and Lisp, A future is an object which represents something which isn't knowable yet, but might be in the future. So you can begin interacting with the future object, and eventually it will communicate your interest to whatever the answer turns out to be. Futures had a big influence on a feature called promises. Promises were discovered in a company that I founded called Electric Communities for a language that we called E. Promises have since escaped from E and moved into Python and then into JavaScript, where unfortunately they've mutated kind of badly. But they're still a really interesting mechanism for managing asynchronicity in distributed systems. The Haskell community is big into monads and arrows. Microsoft has something called RX, Reactive Extensions, which allows for composing of event streams. Very interesting stuff. Unfortunately, it's never been documented documented sufficiently.
We do have a course by Jaffer Hussein, which covers essentially the observable pattern and how RX kind of works and everything. Just throwing it out there. Yeah,
it's good stuff. It's just I wouldn't use it because if I'm putting it into production, I want to know how it works. But it's been inspirational. It's created a new form of programming called functional reactive programming. Examples include Flapjacks, Bacon and Elm, and others. But it occurred to me that this list just isn't long enough. So I'm adding my own thing to it, and that is a library called RQ. RQ is a library for managing asynchronicity in server applications. The thing that distinguishes it from the others that I mentioned is that this one was designed specifically for what you do in servers. None of the other ones were. Everything can be made to work, but I think for what you do in servers, this one's going to work better for you. So RQ is a very small library. It only contains 4 or 5 methods, depending on how you count. If you count in Java, it's 5. If you count in JavaScript, it's 4. So let's look at the 4, because once you do these 4 functions, that's the whole thing. So a sequence takes an array of requester functions and returns a function that will call them one at a time, passing the result of the previous requester to the next requester. So here, for example, we're going to make a getNav requester, which will first read the file and then get the preference and then get the custom nav. Then we can do things in parallel. Now, we're not adding parallelism to JavaScript. What we're doing is allowing JavaScript to exploit the natural parallelism of the universe. Because it's likely that you're going to be calling services that are in different boxes or different networks. It's all going out, and the universe runs asynchronously all the time, so you get to take advantage of that. So here we're going to make a getStuff constructor, which will, when it's called, get the nav, get the ads, and get the message of the day. It'll get them all at once. So the cost of this will be whichever these 3 is the slowest. Then we can also have optional things. So we can provide a second array of optional things. So we will also go and get the horoscope and the gossip, but we will not wait for those. If either of those doesn't complete before the main 3 complete, we'll just cancel them and return with whatever's been finished. We can deal with races. These are the good kinds of races. So we can start several things at once, and whichever the first one to finish successfully, that's the one we get. So we might be having trouble with our ad network. We're dealing with 3 ad networks, and they're all too slow. So we tell them, we're going to have a race. Whenever we have a position, we will ask you and 2 of your competitors, and whoever comes back first with a suitable placement will win. We can also deal with fallbacks. So we can try one thing. If that fails, we'll try another. So we're going to do that to get our weather. We'll first go to our local cache. If that fails, we'll go to our local DB. If that fails, we go to the remote DB. Now, in theory, the fastest way to get the weather would be to have a race. But the whole point of having this kind of hierarchy is that we want to go to the remote DB only as a last resort. And fallbacks allow us to do that. So that's it. That's the whole matrix for RQ. We can start all the requesters at once, or we can start them one at a time, and then we can then take one result, or we can take all of the results. This is an example of an RQ program. You can write RQ in the form of nested arrays, which describe the work that you want to do with the calls to RQ acting as annotations as to what happens in parallel, what happens in serial. So here we've got one request that's going to do stuff in parallel. In parallel, it's going to do a couple of sequences and then one standalone thing and a race and a fallback. And simultaneously, it will also do this optional set, which is a similar set of stuff. And when it's all done, we will then call this function, that's the continuation, which will show the result. So this is an actual JavaScript program, so let me execute it so you can see what it does. So each of these widgets represents some service which is being accessed by that program. So those are the ones that start immediately. And I get to decide which of these are going to succeed and which are going to fail. For example, if I have that one fail, then the entire request failed, and you can see I canceled everything else because we don't need it if the whole job's not going to work. So let me reset and we'll try it again. So let's say this time that one succeeded. Okay, we're still running. Things are good. This one is optional. Let's say it fails. Okay, it failed, but no problem. It's optional, so we're still running. Let's say this sequence starts or is successful. Good. So then A2 started. We got the request A1 finished, so A2 starts. We do a similar thing with B1. That succeeded, so B2 is now running. We've got a race with D1, D2, D3. Which one should win? 2. So race 2 wins, and we cancel D1 and D3 because we don't need those results anymore. Let's say our fallback fails. Not a problem. The next step in the fallback succeeds. And I can finish these in any order. So let's say that goes, and maybe that succeeds, and that succeeds, and that succeeds, and we're now good. So at that point, the whole thing finished. All of the optional things that were still pending, those got canceled, and we're done. Any questions about that?
Yeah. Could you give us a real-world example of where you use this?
Yeah, I will. I've been sort of doing that. So I gave examples that we get the nav and we get the ads and all of those. Those are real-world things. Those are the sorts of flows that you would have in a web application.
So you maybe want 3 ads, but any of 12 could load there. You'll just take the first 3, or
sure, you can do those sorts of things. Whatever you need. So this again is the program that accomplished that. All of that behavior happened just in the RQ functions handling that stuff. So, and you can compose these things in lots of ways. For example, this is a sequence in which we'll do one thing and we'll take its result and we'll pass that to 3 different things, and then we'll accumulate all of their results into an array and pass that array to the last one. So you can get lots of workflows. So for a real-world example, this is the most recent thing that I've been working on. I'm working on an encyclopedia, and I'm writing in a authoring language, and this is the process that I run in Node for building the book. So I first read the file, and I call then I pass that result to the include processor, which handles the stuff with all the include files, and then I pass it to a thing which will then compile it and produce the HTML, and then I have another thing which will then write it out to the file system. So this is a sequence. One thing happens to another, but it's not being written as nested event handlers. It's written as a list of things that happen, one thing after another. So it looks more like a program.
What's the callback? Is the callback the next function, or?
The callback is similar to the thing that we did with continuize this morning. It's the thing that will receive the result. So this is a special case of continuation passing style, where at each step we don't return the result. Instead, we pass the result to a function that's provided to us.
And the final callback is essentially the console log?
Yeah, the last one will send it to the console.
Okay, but this is your program, right?
Yep.
Where is so this first function, It's a sequence. First it's going to call the first function, then it's going to call the second function, then the third, then the fourth.
Right.
Where's the value of callback that gets passed into the first function? Where's that come from?
It'll be called by, so what I didn't show here is that RQ sequence returns a function. When we call that function, it will then call the first in this list, providing a callback function to it.
And that's the hook that makes it call the second one.
Right.
Sort of RQ sequence kind of always passes itself into each of the functions that it calls.
Sort of, yeah.
Okay.
It passes the value from the previous callback.
Yeah,
Okay. You mentioned that earlier, yeah.
right. So you can think of it's sort of like a pipe,
Yep.
you know, that's passing this stuff through, so each gets the thing from the previous one.
And this is not Node. This is just pure JS.
Right, this is pure JS. You could run this in a browser as well. If
Right.
you've got asynchronous things to do there, it would run as well.
And it's not a module.
It's just
a global. RS would be a global, or wherever you declare it.
It's just a JS file. You can load it however you want.
It's just JS. It creates global, though, called RS. Your global namespace.
In a browser, it creates a global namespace. In Node, it will add
Be a
some.
module.
Yeah, it'll export as a module.
Okay.
So RQ can also deal with timeouts. So each of those functions will also take a time in milliseconds, which says this needs to complete successfully in this much time, or we will fail it. And in the case of the parallel, you can also specify untillaseconds, which gives the optional set, you've got this much time until you get canceled. So just in case the main ones finish early. Then we can also deal with cancellation. So any requester function can optionally return a cancel function, and that cancel function, when it is called, will attempt to cancel the request. There's no guarantee that the cancellation will happen before the request completes, because there can be network races and other things going on. So it's intended to stop unnecessary work. It's not an undo. It's not a rollback. You know, so if you're trying to cancel a transaction, for example, this is not the cancellation that you want to do. RQ has 4 types of functions in it, and if you can manage these 4 types of functions, then it's pretty easy to use. We have requester functions, which are functions that can execute a request. We've got callbacks, which are continuation functions that are passed to requesters. That's how a requester returns its result. We have factories, which are like the factories you've been making, which make requester functions. They act as a convenience. In fact, the 4 functions that I've shown you are all factories. And then cancel functions. A cancel can be returned by a requester to cancel a request. So a callback function takes 2 parameters, a success parameter and a failure parameter. So if success is undefined, then it fails. And if failure is undefined, then it succeeds. And there's just one callback. In promises, for example, there'll be 2 callbacks, one for success, one for failure. I think it's easier if you just have one. Then a requester function will take a callback and can optionally also take a value. And that's how a sequence will move results from one step to the next. A requester function can return a cancel function, which is used for cancellation. And factories make requesters. So that's the relationship of the 4 kinds of functions. So let's look at an example. This is the identity requester. This is the simplest possible requester. It will receive a value, and it will then send the value to the next thing in the sequence. So if you put this in the middle of a sequence, it's a do nothing. It'll just take whatever is going on and give it to the next one. You would never do that, but this is the model for the simplest form. Then this is, so we can wrap those things, or I'm sorry. This is the full name requester. This one receives an object containing parts of names, and will concatenate them together to make a name and then deliver that to the callback. So I could add this as a processing step, for example. And we can write functions which will automate that for us. So requesterize is similar to functions that you've been writing. It will produce a requester that will call some ordinary function. So we can take any existing function and turn it into a requester, which could reduce the amount of work you have to do in transiting to RQ. This is a delay requester. This is the simplest real-time thing. You would never put a delay into a server application. What you would do in a real situation is, instead of calling set timeout, you're going to send a message to some service. And instead of calling clear timeout, you would send a message probably to the same service telling it to please stop. So you just make the substitution. But if you were to take the delay requester and put it in a sequence, the sequence will run exactly the same. It'll just take longer. But it'll take longer without blocking. Then this is the delay request, or the delay factory. So this code is the delay requester, except the factory is providing the milliseconds value.
These are all part of RQ?
No,
Or
these are examples of how you could use RQ.
Things that you put in there, okay.
Yeah, none of this code is in RQ.
What does RQ stand for?
Request. Then this is a factory for reading files. So this factory will produce a requester which you can then put in a list which will then read files for you. And this one is wrapping the node file system. This is the widget that was in the demo that I showed you earlier. This is all HTML crap, so I'm not going to bother you with that. But and I did it this way because I didn't want to have to depend on any one library, because if I chose a library that's not everybody's favorite, and it turns out everybody is not somebody's favorite, so it's just DOM, so it's awful. But the interesting features here are that this is the click handler, or the success handler. So when I clicked on yes, on success, I changed the color of the widget to green, and I called the callback to let it know that it finished successfully. And on the failure side, it was similar, except I set the background color to pink, and success is undefined now to indicate that we have a failure result. And in the case of cancellation, I just set the background to gray.
Why did you reverse your success failures from the convention in Node?
Because Node got it wrong.
Because they got it wrong?
Yeah.
Okay, I agree that it seemed really weird, but now you start to use Node for a while and you encounter people who do it the right way, it seems weird.
Yeah, exactly. And I know I'm introducing a hazard. Doing things right in a system that does things wrong is going to, yeah, and I understand that, and I apologize for it.
Okay.
I just couldn't bring myself to do it the wrong way. Let's talk about testing. So testing in asynchronous systems is tricky, because most test frameworks come with stuff like this, right? You've got some assertion, and you've got a descriptive message, and something, you'll have an expected value and an actual value, and if they match, then it's good, and if they don't match, it's bad. Except this doesn't work in asynchronous systems, right? Because you can't wait for the actual value. The actual value might not happen until many turns into the future, and this just doesn't work. More than that, though, I have a problem with the way we do testing in general, in that we're trying to guess what the expected value is, which is going to identify the bug. But most of our errors happen in the interactions of things, and finding where a bunch of things are going to come together and interact at the one point that fails. It's virtually impossible to find that one point. So what you really want is to have a grid, right, a dragnet, where you're going to have a much larger array of spaces that's distributed randomly over the possibility space, and you pick them all out, and hopefully then you'll improve the likelihood that you're going to find the error. Except you don't want to do that, right? You don't want to have to write 1,000 times more test cases, most of which are unlikely to succeed in finding anything anyway. That's a huge amount of effort. No one's going to want to do that. Plus, if there's a model change, it means you now have to update thousands more tests, and nobody's going to do that. And I was kind of despairing about that when I saw a talk by John Hughes of Chalmers University about something called Quick Check, which I thought was brilliant. So to give you the context about that, Quick Check was developed in Haskell. Haskell is a language that was developed at the University of Edinburgh, and it is a pure functional programming language. They say pure in that it's a language without side effects. And that's good and bad, but there's good things about it. The other thing about Haskell is it's got maybe the best type system of any language in the world. Instead of having something like in Java where you specify the type of every little thing, you specify the types of almost nothing. And instead there's an inference engine that runs as part of the compiler, which goes through looking at everything in the program, trying to determine what everything is. You know, if you're one of those and you interact with that, then you must be one of those, and so on. And we'll keep doing that, trying to solve the entire program. And if it gets to a point where it finds an inconsistency, it can stop and go, you know, something's wrong here. And the difficulty with that is that where it finds its inconsistency may be miles away from where you actually made your mistake. And so getting a program to compile can be really challenging. But the theory is that once you get a program to compile, it's guaranteed to run. Except that it's not, because it turns out the class of potential errors is infinitely bigger than the class of errors that can be found even by the world's best type system. So you still have to test. And these guys came up with a really nice way of doing tests. Instead of writing specific compare actual versus expected, instead you write a function which will be true if the system is working correctly. So, and they call those properties, that the system will be true, is working correctly if these properties hold. And so, and then Quick Check will generate random data and throw them at your functions and try to disprove your assertion. And so they can get tremendous coverage. They're even able to debug real-time systems, which is something that is really, really hard to do. So I thought, wow, we should get one of those for JavaScript. So I wrote one. It's called JS Check. JS Check provides two nice things. One is case generation, so it'll generate random test cases for you. And it also supports testing over turns. So you can use it to test stuff in Node, you can use it to test things in browsers, you can use it to test synchronous and asynchronous functions. So it's a small library that comes with some functions. These are a few of the interesting ones. The most important one is claim. We'll talk more about that in a minute. That's where you make a claim about the system. If it's working true or working correctly, then this will be true. You can then tell it to check all of the claims that you've made so far. And you can also put a time limit on it. So it'll start all the tests simultaneously, and they all have to finish by a certain amount of time. If they don't, then you can record that. And that's really important, because the way our systems work now, getting the right answer but taking too long is indistinguishable from the wrong answer. And so we need to be able to test performance as well, and that's something that the synchronous testing frameworks don't do. Then we can get a callback when the thing is done, and we'll get a full report about everything that happened. We can also get a callback on each error as the errors occur. And you can program that callback to take you into the debugger. So as you're finding bugs, you're in the context where you can fix it immediately. So this is the claim function. It takes a descriptive name. It takes a predicate function, that is a Boolean, which will be true if your system is working correctly. And it takes a signature, which is an array of type descriptors, which describes the parameters to the predicate function. So here's an example. We're going to compare the old code with the new code. Our predicate will take a verdict function and an argument, and we will then determine that the old code for that argument does the same thing as the new code. And we tell it that that argument is an integer. So when we tell this thing to check, it will generate random integers and throw them at that function, trying to disprove our assertion. And you can set as many as you want. So all of the effort in using the system is in writing these predicates. And there are lots of ways you could do it. One is to, in this case, we're comparing the old code against the new code. So we're, as we're migrating the system, we can make sure that we haven't changed the behavior of anything. Another way you could do it is if you have symmetrical operations. For example, if you're writing an encoder and a decoder, it's usually the case that the decode of the encode should equal the original thing, so we can test that that's actually true for a large class of trials. We can generate symmetric pairs of things, like we can generate a credit and a debit, both using random values and make sure everything balances. And in some cases, you just might throw a lot of random transactions at something, and after each one, run a deep diagnostic of all your data structures, make sure everything is still consistent.
So how would this look like implemented? I don't understand where verdict is.
We'll get to verdict in a minute.
Okay.
So verdict is the callback that is being used in the cases.
Okay.
So it comes with a small library of specifiers. You can put each of these in the descriptor array of what types we want to throw to our predicate, and it'll try, generate values, random values of each of these types. So if you need booleans, if you need integers, numbers, objects, whatever, it'll make random things and pass them out. If it turns, and these are also composable in interesting ways. For example, if you want random social security numbers, I can say I want a string with 3 digits and then a dash and 2 digits and a dash and so on. Or if I need an array containing 3 elements where the first element is an integer and the second is a number between 0 and 100 and the third is a 8-character string, I can get that. Or I need an object with a left property, a top property, and a color selected from a list. Or I need an object with a variable number of properties where each property is a 4-letter name and each value is a boolean. I can do that. There are lots of ways to compose these. And if it turns out there's some particular test data that you need that's not easily composed from these, you can write your own. And it's a generator, exactly like the generators you've been writing. So you have a function that returns a function that each time you call it, you'll get the next value. You can write one of those to generate all the random test data that you need. Then the reason this works asynchronously is because of the verdict function. Every check, when it begins, is passed a verdict function that it is used to return its result. And the verdict is just a continuation, it's just a callback, which allows the trials to be extended over many turns. And because we can also put time limits on this, we now have 3 possible outcomes for every trial. We can see a pass, we can see a fail, or we can see a lost. Lost means we did not get a report before the time expired. And those are sometimes as important as the passes and fails. Both of these systems, RQ and JSCheck, make tremendous use of closure and continuation. And the really great thing about working with closure and continuation is that they make you feel really smart. I mean, you noticed this, right? Yesterday, you've been doing a lot of work with closure. It makes you feel smart. When you get these things, it's like, So, and everybody deserves to feel that way. You know how people who do a lot of functional programming are always acting like they're so much smarter than you are? They're not, but they're working with this stuff all the time, and it makes them feel good all the time, makes them feel smart, and that's a really good way to feel. Everybody should feel like that. Whereas the stuff you're working with every day, does it make you feel smart? No, it does not. So you want to get a hold of this stuff. It's great. So both of these projects are public domain. They're both on GitHub. They're both totally free. If they can help you, go ahead and take it. There's lots of other good stuff in the world too. If that is better suited to you, use that. So any last questions about RQ or JSCheck or asynchronicity? Yes?
There's a couple that queued up here. One, he was wondering if you've checked out Elm, since the type inference is the same as Haskell.
Yeah, I mentioned Elm earlier. There's good stuff. Everything in that list is good. But I think our queue is of interest to you because it is the best suited, I think, to the workflows that you have to implement. Anything else?
There was one from earlier from the security section. He just wanted you to clarify, or he was asking, we're learning about objects and security and how to prevent attacks, but isn't this something that servers are supposed to deal with?
It's something everything has to deal with. It's not so much the servers, it's us. It's the people who are writing the programs who have to deal with this stuff.
Yeah, a little bit more specifically though, what is the, it sounds like we're talking about, you have an object and you don't want some other object to attack it. This has to do with mashups, right? Because you want to lend out your code to somebody else and you want to make sure that they don't infect your code.
I want to strengthen everything. So if I can make my code strong enough that I can run it with third parties, which is the thing that we want mashups to be able to do, I can be confident that it's going to work with my coworkers' stuff as well. That most of the attacks that are bringing our systems down are self-inflicted, right? The stuff that we do to ourselves because we just didn't get it working well.
Because you're not saying if you're not doing mashups, don't worry about this.
No, we need to worry about this all the time. Everything we write should be to that level of quality. Everything. And now the better parts. So this is Antoine de Saint-Exupéry. He was an aviator back at a time when aviation was really dangerous. That's what we used to call pilots, but he was an aviator. It was really dangerous because the planes crashed. And he experienced several crashes during his career, survived almost all of them. He was once trying to set the airspeed record from Paris to Saigon, and his plane crashed in Egypt, near Cairo, out in the Sahara Desert. And he was not prepared for survival in the desert. He did very badly there, suffered terrible dehydration, dehydrated so much that he stopped sweating, which is a really dangerous thing to do in the desert, suffered terrible hallucinations. Fortunately, he was rescued by someone who understood how to treat severe dehydration, and he survived and recovered, moved to America as the war is beginning, becomes a writer. And he turns out he's a brilliant writer. He writes one of the most famous children's books, The Little Prince, which is about an aviator who's stranded in the desert, who is visited by a strange little boy who lives on an asteroid and is suicidal. Like all the best children's books, it's not really a children's book, yeah. And he wrote other books too. He wrote some very good books about aviation, books aimed at grown-ups. In one of them, he has one of the best sentences ever written. He says, "It seems that perfection is attained not when there is nothing more to add, but when there is nothing more to subtract," which is just brilliant. I've seen this quoted and requoted over and over again. It's used all over the place in engineering, design, anything that's creative, that requires some kind of discipline. It's just a brilliant quote. And he's talking about the design of airplanes, but it seems to talk about everything. And I think it's especially telling for programming, because we have a special relationship with perfection, right? That our programs have to be perfect or they're not going to work correctly. And he gives us some insight as to how perfection is attained. It's by removing things, it's not by adding things. And I think we can also apply it to programming languages, because we have similar things going on there. That most of our programming languages tend to want to add things, but I think most of them could be improved by removing things. And that's where the principle of the good parts comes from. That if a feature is sometimes useful and sometimes dangerous, and if there is a better option, always use the better option. And it surprises me that this is a controversial statement. You know, there are lots of people out there who say, I don't want to use the better option. You can't make me use the better option. It's like, being better should be enough, but it's not. And I think that comes from a fundamental misunderstanding about what it is that we do. We are not paid to use every feature of the language. At the end of a project, there is never a manager with a clipboard saying, did you use a with statement? Did you leave out any semicolons? Did you use comma as an operator? Excellent. Nobody's doing that. We are paid to write programs that work well and are free of error. That's what it's all about. Now, free of error, where did that come from? Well, it turns out free of error has always been the first requirement. It's just we so rarely attain it, it's easy to forget that it's the most important thing.
That's why I never gotten paid, I guess.
So a good programming language should teach you. I recommend everybody learn as many languages as you can, because every language will give you some new perspective on something, maybe push you into a new paradigm, and you can take the things that you learned and apply it to all the other languages you know. Everybody should learn as many languages as they can. And the language in my career that has taught me the most has been JavaScript. And it took a while for me to learn from the language because, well, I made every mistake in JavaScript that you can make. Starting with the first one, the worst one, I didn't think I needed to learn the language before I started writing in it. That I had so much contempt for it. The first time I saw JavaScript, I thought it was the stupidest thing I'd ever seen. And it turns out I wasn't completely wrong, but I wasn't completely right either. Eventually, I was cursing all the time I was writing in JavaScript. It made me very, very angry. And eventually, I decided to learn the language. So I got the standard, which you can get free off of the ECMA site, and read it and was surprised to discover that it had lambdas in it. It had functions with first-class values with lexical closure, which I had no idea that it was in there. Brendan put it in there intentionally. That's not something that gets into a language by accident, but he didn't tell anybody. And so I discovered it in reading the standard and was like, wow, this changes everything. And at that point, my relationship with the language changed. And at that point, it was able to finally start teaching me things. And it has taught me a lot. So one of the things I did with JavaScript was I wrote JSLint because I needed a tool to help me avoid all of the traps that are in that language that are there to defeat me. And JSLint, turns out, is much smarter about JavaScript than I am. My initial intuitions about what were good features of languages and what were bad were extremely unreliable, whereas JSLint was very good at always directing me to the correct point of view. What is it that we can do mechanically in order to find mistakes? Because that's what I need to do in order to try to make my programs more perfect. And JSLint has taught me an enormous amount about programming. And so I wrote my own book about my experience with JavaScript and with JSLint, which is called JavaScript: The Good Parts. And the surprising thing about this book is it is still a bestseller in its category, which is extremely rare for software books. Most software books are obsolete before they're printed. And it's because things tend to change and roll over so quickly in software. But it turns out the things that I was saying in this book are for the most part right. And so, it's still a relevant book, even though JavaScript has gone through 2 major standard revisions. This book is still pretty good. So it's not universally adored, though. There are lots of arguments against the idea of good parts. I'd like to run through some of those, if I may. The first one, it's just a matter of opinion. It's your opinion. My opinion's different. One opinion's as good as another, so there. Turns out that's not the case. That I am the maintainer of JSLint, and as such, I get bug reports from people from all over the world telling me, I just spent 2 weeks chasing this thing down, and it was due to some weird edge case in the grammar of the language that no one had ever noticed, and it just crippled us, hurt us at a bad time. And could you have JSLint look for that? Because if you can, then no one else will ever have to endure that. So whenever it makes sense to, I incorporate those things. So if you're using JSLint, then you will never experience those things. That is not an opinion. That is a fact. Every feature is an essential tool. I need every tool available in order to do my work. But that's simply not true. We can show that you can write better programs by not using all of the features. So if you can write a better program without using a feature, that feature is not essential. But this feature is sometimes useful. And that sounds like an important thing. I need to be able to use it because it's sometimes useful. Except it turns out everything is sometimes useful. You cannot identify anything which is so dangerous, so toxic, so disgusting, that is not also sometimes useful. So sometimes useful is about as strong a statement as it exists. It sounds like it's a lot more than that, but it isn't. It actually is not an argument. So if the reason for using a feature is because it's sometimes useful, you simply do not have an argument. I have a right to use every feature. Now at this point the argument has changed. We're no longer talking about what's the best way to write programs. We're now talking about our rights. And it sounds really important and righteous to be talking about rights and defending and blah, blah, blah. Except if you follow this argument to its conclusion, ultimately it goes like this. Do you have the right to write crap? Yes, I have the right to write crap. So now we're arguing about, do you have the right to write crap? Is that true or not? I don't know. I don't care. It's not important. What's more important is you have a responsibility to write code that works well and is free of error. I need the freedom to express myself. I'm a poet, and the way I express my poetry is by leaving out my semicolons. I need to reduce my keystrokes. This is a really insidious one, again, because we imagine that we spend most of our time typing, but we don't. You know, so if you were to take all the clean finished code you finish in a year, you could type it in a day. So that raises the question, well, what are you doing with the other 99% of your time? Keystrokes is not the important thing. If I could figure out a way to increase your keystrokes by a factor of 10 and cut your errors in half, that would be a huge win. Unfortunately, I don't have that formula for you, but that's the sort of ratios we're looking at. It is an insult to suggest that I would ever make a mistake with a dangerous feature. You know, inferior people could obviously have problems by doing that, but I must have satisfaction. And then there's a good reason those features were added to the language. And I can tell you from experience, that is absolutely not true. I've seen how things get put into languages, and that those things happen for all kinds of reasons, and they're not all good ones. The creator of JavaScript, Brendan Eich, talks about foot guns. A foot gun is a feature of a language that you use to shoot yourself in the foot. And he put a lot of those in JavaScript, and I think he regrets it. And from time to time, he would tell the standards committee, let's not be adding too many more foot guns. They don't always listen to him, so you can always find more. But they're, guys, look. Oh, I almost always miss. Watch this. So the purpose of a programming language is to aid programmers in producing error-free programs. That's the whole deal. So we used to think that it was not possible to write good programs in JavaScript because the language was such a mess that it just wasn't possible, so no reason to even try. It turned out that was not true, that it is not only possible to write good programs in JavaScript, it is necessary. It is so easy to go off the rails with this language. It requires tremendous discipline, maybe more discipline than any other language. So you really have to bring it when you're using this language. So there's a lot of confusion still about Java and JavaScript because they kind of look similar and they have the same name. Sometimes I'm introduced as a Java expert, which I am, but I'm usually invited because I'm a JavaScript expert. And it's similar to the confusion we have between Star Trek and Star Wars. You know, we've got two science fiction franchises with basically the same name, and you know, from 10 feet away, they kind of look like the same show, but we know they're not the same thing, right? The differences are really significant. In Star Trek, you got phasers and photon torpedoes, you got uniforms, damn regulations, everything's regulations, right? Whereas in Star Wars, you've got lightsabers and blasters, you got proton torpedoes, completely different torpedoes. You got sand, I don't like sand, and chaos. So, you know, which one of these is JavaScript? Well, obviously Star Wars, right? In fact, when you're working with JavaScript, JavaScript presents you with a choice. You can go Jedi, or you can go Jar Jar. And, you know, quite a lot of our brothers like to go Jar Jar, so. So one thing I've observed, or two things I've observed, are the fantasy of infallibility and the futility of faultlessness. I see the fantasy of infallibility, especially in younger guys who think they have such mad skills that they can write just any crap and they're going to get away with it, that they can just do stupid and it's going to be all right. Then the futility of faultlessness, I see this more among older guys. Guys who've been doing this for a long time, never seen it go right. It's never going to go right. Why even try? You know, it's just so two very different perspectives, but they both lead to the same thing: danger-driven development, where you're doing crazy, reckless stuff in the code just to keep it interesting. Because anyway, don't do that. Oh, and don't forget your semicolons, right? So one of the things that makes programming difficult to manage is the difficulty of scheduling. That usually when we're doing something, we're doing it for the first time we've ever done it, and so we don't know. There's no way we could know how long it's going to take. But we'll make guesses, and our guesses, because we're optimists, are usually wildly wrong, but that's the way it goes. But what's even harder is scheduling the second time, which is the time B, the time it takes to make the code work right. Now, that should be 0, right? You should write it, and it should be right, and we're done. But that's not the case. That often time B is greater than time A. I've seen cases where time B is infinite. That's what happens when the code's finished, but then the project is canceled before they can get it to work. That happens way too often, actually. So if you do anything in time A that increases the likelihood of time B being bigger, you're doing it wrong. That's not the time to be saving time. So we should always take the time to code well. Sometimes there's this idea that, well, we're just doing this quick and dirty thing, so let's just be really sloppy and get it done fast. Except getting it done still means it has to work. And getting it to work is still going to be easier if you write it well. That the time it takes to write it well is going to be less time than it takes to make it work right if it's not written well. We've got a new version of JavaScript that was approved by the General Assembly 6 months ago, and many of the features of it are already in browsers now, and some of them will be coming in later. And so this is a good time to look at what's in the new language. Did we get any good stuff in it? And the answer is yes, we've got actually a lot of good stuff in it. So my number one most favorite new feature of the language, proper tail calls. So the compiler will turn that into a jump instead of a call return. So it'll go a little faster, take less memory in getting there. It enables continuation passing style and other modes of programming. It's great. So that's my most favorite feature. With this, JavaScript finally becomes a real functional programming language, which is great. My second most favorite new feature, the ellipsis operator, which we talked about quite a bit yesterday. Again, there's two versions of the query function. There is that one and that one. They both do the same thing. This one's inexcusable. This one's actually pretty nice, so that's going to be a good thing. We've got modules in the language now. Unfortunately, the module system we got is way too complex, but it works. So there's a subset of the module system which is adequate, which is you just want to say, here's some stuff. I'm going to export this thing. That's how you use it, and that's all it needs to be, and it can do that. So that's good. That's much better than requires or any of the other module loaders. We've got let and const, which by themselves are not that big a deal, except they are less confusing to Java programmers, so it's good not to confuse the Java programmers. So I like that. One thing I find confusing about this is that I've seen a lot of developers are confused about the difference between const and freezing. And so they're surprised that you can put a mutable object in a const and still mutate that object. So const is for variables, freezing is for values. Just remember that, it's pretty easy. We have destructuring. Destructuring is something you can do in let and const statements and also in assignment statements, where we can create new variables and initialize them from some object at the same time. So again, not a big change. Doesn't let us do anything we couldn't do before, but it is a convenience. Yeah.
I think you said freezing is for values. Did you mean freezing is for objects?
Objects are values.
Okay.
You
Yeah.
could, in theory, you could freeze numbers, except they're already frozen, and strings are already frozen, so you don't need to freeze those. But you can,
One follow-up. What about nested objects?
it only freezes the outer one.
Right.
There is no deep freeze in the language.
So you have to do a recursive
If you care about that, you have to
freezing.
descend into the language and freeze each level. Then we have weak map. Weak map is a really nice thing. Weak map works the way objects should work. With a weak map, you can take any JavaScript value and use it as a key, and then associate any other value with it, which is the way objects should have worked. And it also has a nice property that it does not root the keys for the purpose of garbage collecting. So if the only place where an object still exists is as the key of a property in a weak map, it will get garbage collected automatically, which is brilliant. So that means there's a class of applications which we can write in JavaScript now using weak map that we could not write in the language before, which is really nice. The biggest problem with weak map is it has maybe the worst name ever put on a feature of a programming language. Because who wants to use something called a weak map, right? Just that, but it's actually a really good thing. It's just a really bad name. And we have megastring literals. So we have the backtick, which we can now use to make literals that can span many lines. So here's an example of a regular expression. This particular regular expression matches all of the number literals that are in ES6. And you can see why I don't like regular expressions, because you can't make any sense out of this, right? Just looking at that, it's just noise. It's really hard to understand what it's about. So I can make things a little easier now. I've got a function here which will call the regular expression constructor, passing it in a string, and but first it will remove all of the spaces from that string. And so now I can use one of these mega literals to write it out with all the white space in it. And with white space in it, regular expressions aren't quite that bad. You know, with got spaces between each of the elements, and I can line them up, and you can kind of see what's going on. So we now have binary literals. You can have 0b followed by zeros and ones, and we've got octoliterals, which I'm still not sure about those. You've got a 0 followed by an O, and then octal digits, and we've always had the hex and the floating point. So that's pretty neat. This is a much nicer way of writing regular expressions. There's still things about the mega literals that I don't like. That backtick is the smallest operator we've got, and it's used to bracket the biggest structures we've ever had. So there's potential for misreading here, so we're going to have to be cautious with this, but I think this is probably a good thing. And again, regex. If you're writing regular expressions, even with the white space, you still want to be using regex. So we've got fat arrow functions, or farts for short. The motivation here, there were people who were complaining that with function you have to type 8 letters. You have to F-U-N-C-N-N-N. I said, that's too much to type. And I said, well, there are these new things now called keyboard macros. And it's too much to read. Okay, so we added them. So it's a short form for writing a function that will return a value. So we got the parameter list, we got name, and then we got the fart, and then we've got the return value after it. So you don't have to write function and you don't have to write return. except this will fail. This looks like it's a little mini constructor that's going to return a new object, right? It's going to return a new thing where the ID is whatever the name is that we passed. This is going to fail. Instead, it's going to give you a function that returns undefined, which is not good. And it's because of a syntactic ambiguity in the language. The committee was aware of this when they did it. We just keep adding new bad parts. We can't stop doing it. So because of that, I'm not a big fan of these.
So it'll compile, but it won't run?
It'll compile, it'll run, it'll return undefined when you call it. You will not get the new object that you're trying to construct. We keep doing this to ourselves. We keep doing this to you, is how that actually works.
Because the brackets are ambiguous?
Yeah, because the brackets are ambiguous. We could have, there are a number of ways they could have disambiguated it, but they decided instead to make them blocks.
Well, because that's not, what you put inside the brackets isn't really the contents of a function. Typically a function would return, I'm confusing this part with what we're using in another language, in TypeScript, I think. Is they put fart in TypeScript, and I've been using it, but I'm using it to call a function to do something.
So this will work for lots of other purposes. The place where it fails is if you're trying to return a new object literal.
You would have on the other side of this var x equals.
Yeah, or you'd pass this, more likely you'd pass this as an argument to another function. That's one of the most common uses for these. So anyway, moving on. And there are lots of other bad parts in the language too, like generators with the yield operator. I think that was probably a mistake. It adds a lot of complexity and not much value and kind of locks people into patterns, which I think are things that we should be evolving away from and not getting trapped in. A lot of the other new features, we haven't had enough experience with them yet to know if they're going to be good parts or bad parts, but there is one part that I'm confident is going to be a very, very bad part, and that is class. This was the most requested new feature for ES6, and it was mostly requested by Java programmers who were having to move into JavaScript and were unhappy about it and saying, please, can you turn JavaScript into Java so we don't have to learn this crappy language? And so we did that, except we didn't actually add class. What we did was we added syntactic sugar on top of the prototypal stuff that's already there. So when you get down into the edges, it's not going to work the way you expect it will. But worse than that is it keeps you trapped in the mindset of the classical model, which means you will never learn to use the functional model. And also you don't have the strong type system that you need in order to deal with classes. And so I'm pretty confident that the people who are going to be using classes are going to feel vindicated. You know, it's in the standard, I have a right to use it, it's all that good stuff and all that. But they will never learn to use the language effectively. They will go to their graves never knowing how miserable they were. I'm also reconsidering things that I had put in the book. Do I still think the things I said were good then, are they good now? So in the book, I didn't recommend use of new. I stopped using it. I recommended using object.create instead. And in fact, I managed to get object.create added to the language just so that I could use it. So I was really surprised to kind of notice that I've stopped using object.create. And the reason for that is because I stopped using this. If you're not using this, then create doesn't do all that much for you. And the reason I stopped using this was because of AdSafe. So in 2007, there were a number of experiments at trying to figure out how to turn JavaScript into a secure language for doing mashups and third-party interactions. There was FBJS at Facebook, there was Web Sandbox at Microsoft, there was the Kaha project at Google, and there was my own AdSafe project. And one of the difficult problems everybody was struggling to solve was, what do you do about this? Because if you have a method, this will get bound to the object of interest, and that's good. But if you call that same method as a function, this gets bound to the global object, which gives away the farm. And how do you deal with that? And so the approach that the other three projects took was they have translators. They read JavaScript and they write JavaScript, and the JavaScript they write is much bigger because they're adding a lot of runtime checking and indirection in order to find cases where this is turning into a global object and allowing bad things to happen. The approach I took with AdSafe was much simpler. I said, this is illegal. So if we see a program with this in it, we reject it. Done. Easy. So we don't rewrite the programs, we don't make them harder to debug or slower to run. If the program passes AdSafe, it gets to run at full speed without any modification. But the AdSafe rules would reject pretty close to 100% of all existing programs in the web. So in order to use AdSafe, you had to work in the AdSafe dialect. So I decided as an experiment, well, I'll work in that dialect. I'll see what it's like and how painful it is. And after working with it for a while, I was really surprised to learn that it got easier. That I expected it was going to be a hardship that I was going to have to get around, but it actually got easier and my programs were getting better. I was forced to use the functional patterns because the prototypal patterns weren't available because I stopped using this, and I really liked it. And so as I've gained confidence in this model, and I've become an advocate now of getting rid of this entirely and going all with functions, because that's where the goodness is. Yeah.
What does JSLint say about this?
So JSLint, this is now an option. So there is now an option that you can specify which will suppress warnings about this. I don't recommend using that option, but it's there. I added options to JSLint for transition, so because over time I'm constantly looking at how can I make this language smaller and better, and things that I thought were maybe a good idea last year, this year I'm thinking I'm not sure. Like this year I'm starting to decide that labeled break is probably a bad idea. That I actually haven't used one in many years, and I think I'm better for not having used one in many years. So that labeled break is on its way onto the bad part list. But there are people who are using JSLint who, when JSLint's rules change, go, we're used to doing that, and we can't do that now. So I add the options so that they can transit out. We can just get by for now, and eventually we'll fix our code. Except what happens is people don't fix their code, and they design their programming style based on what options they can turn on. So I'm trying to remove options now from JSLint as much as I can. But I recently added this option so we can transit out.
You don't use prototypes at all. You don't use prototype at all in the code you write.
I am not using prototypes anymore.
So Ben pointed out yesterday that one of the drawbacks to functional versus objects is that all your functions, every function you have, then there's an instance of that function. That's functional programming.
Yeah, we're going to talk about that. That's coming up next.
Okay. I was going to say, are there any other drawbacks to
Nope.
abandoning prototypical?
That's the one.
Okay.
So I've stopped using null. JavaScript has 2 bottom values, which is at least one more than it should. And so I'd stopped using null. I just use undefined now for everything. Even though it's longer to type, that doesn't matter. And I stopped relying on falsiness. I used to think that falsiness was a good idea, and I advocated having comparisons in ifs that were as small as possible. I now think that was a mistake, that we should be trying to make comparisons that are as explicit as possible, trying to intelligently bifurcate the true cases from the false cases. I've stopped using for, because in ES5 we got for each and every and map and all those others, and those are great. So for most purposes I don't need to use for loops anymore. I don't use for in because I managed to get object.keys added to ES5. So for in never worked correctly anyway, because it would always dredge through the prototype chain and you get all the inherited methods coming up, which you would then have to filter out. For in never worked right. So ES6 will have proper tail calls, and when we get that, I will stop using while. So here are 2 versions of the repeat function. Repeat takes a function as an argument and will call it until it returns undefined. And that's a version written using a loop, and that's a version using tail recursion. In ES6, these should both run at the same speed, both consuming the same amount of memory. So this will probably be the last feature implemented in ES6, so I'm still waiting for it. But when it comes, then I'm done with loops. I'm going to be doing tail recursion from here on out.
What does, under the hood, what does tail recursion look like in order to prevent from having this like extremely long stack?
It's really simple. It's just this turns into jump to, it's like a go-to with an argument list. So we jump to the repeat function. So we're jumping to the top, and if this has a new value, which it doesn't, the new value would get assigned up here, and we go again. I've been thinking a lot about the next language. What's the language that replaces JavaScript? And I really hope there is a next language, because if JavaScript is the last programming language, that would be really sad, wouldn't it? I mean, for our kids, right, we need to leave them a better language, right? We can't allow JavaScript to be the last language. So something is going to have to succeed it. And I've been searching for the next language, you know, and what are the signs? How will we know when it's here? You know, it's sort of like awaiting the Messiah. You know, how do we know? And I don't know, but I'm looking for, and I'm starting to try to understand what it's going to be. I'm confident it's not here yet. Actually, I don't know that. It might be it's here, but I just haven't recognized it yet. That, but you know, there are people who tell me, oh, it's C#. Go, no, or it's Java. It's been here the whole time. No. The next language is another language. And it's the thing which is the right thing to replace JavaScript. And we haven't seen it yet. But I think a lot about what it's going to be and what it's going to do. I am confident that when it arrives, we will reject it out of hand, as we always do, because programmers are as emotional and irrational as normal people. We think that we're not. And maybe our spouses tell us we're not, but it's true. We are. And most of what we think about what we do is based on emotion and not on reason, even though we imagine it's the other way around. So this sounds like a wild charge to make of my own profession, but I have some good reasons for saying this, and I think the historical record backs me up on this. For example, it took a generation to agree that high-level languages were a good idea. Back in the early days when everything was in assembly language and the first higher-order languages were being developed, Fortran, COBOL, and so on, who would have most benefited from use of those languages? The programmers. Who was it who was opposed to those languages? It was the programmers. They were complaining that the languages were taking control away from them, that they didn't give them the performance that they needed. They had all of these reasons for why they wanted to stay down in the muck, that they didn't want to be elevated in these more expressive, productive languages. It took a generation to agree that GoTo was a bad idea. Dijkstra publishes his letter in '67, and that starts an argument that literally goes on for 20 years. And the arguments were all silly arguments. There were, you know, we need the performance of the GoTo. It's how I express myself. I can't be me if I can't use GoTo. We have a GoTo tradition. My grandfather used GoTo. You know, you can't take my cold, dead hands. You know, all of those arguments were all made about GoTo. It took a generation to agree that objects were a good idea. So objects are first discovered in Simula in Norway in 1967.
Under the ice?
I'm sorry?
Under the ice. You said they were discovered.
Well, in Norway.
Under the ice?
No, in Oslo. And as always happens with the really important innovations, the world took no notice at all, except for one guy, a graduate student at the University of Utah, Alan Kay, who then takes this idea to Xerox PARC in California, thinking that this idea of objects is so incredibly powerful that he can use it as a programming language for children, that children can use to program their personal portable devices. There was a lot of his vision which was right, a lot of his vision we haven't caught up to yet. We still don't have the language for children, I don't think we have a language for adults yet, but we're still working on it. But they then spent a decade developing that language and did a brilliant, brilliant job of it. And so, in the late 80s, the industry had a choice. We're going to go into object-oriented programming. It took a long time to get there, but we're going to do it. Are we going to go with Smalltalk 80, one of the best designed programming languages in history, or are we going to go with C++? And the decision was made by people who fundamentally did not understand object-oriented programming, and they chose C++ because in order to use that language, you did not need to understand anything about object-oriented programming. That language got some things fundamentally wrong about object systems. Unfortunately, the language has been extremely influential and has set the mold for virtually everything that's happened ever since. I don't know if we're ever going to catch up to Smalltalk. Then it took 2 generations to agree that lambdas were a good idea. So Alan Kay, who was the Smalltalk guy, he started by writing a little program in Nova Basic on a Data General mini computer, which demonstrated his weird little language. And he started touring with this idea, taking it to labs and universities. And he visited MIT, very smart guys at MIT, and he's telling them about his new language. But it's still early in object-oriented programming, and he doesn't have the vocabulary that we have now to describe what's going on. So he couldn't say, you invoke a method on an object, because nobody knew to say that yet. So he described it as you send a message to an object. Well, the guys at MIT listening to him said, well, you're not actually sending a message, you're making a subroutine invocation with indirection. But what if you did send a message? And that started research in the actor model. In the actor model, you actually have these entities that are running in separate systems that can send messages to each other. That's basically what actors are. And the guy who came up with this, Carl Hewitt, is one of these guys who's so amazingly smart. It's like he was born on the other side of the paradigm shift. When he talks about stuff, people cannot understand what he's saying. He's very clear, he's very eloquent, he speaks really well, but he's talking from a frame of reference which is so foreign to the rest of humanity that nobody understands him, including the other people at MIT. They were all very smart and they all had a lot of respect for Carl, but they couldn't figure out what he was raving about with all these actors. So a couple of them, Sussman and Steele, decide we need to build something in order to understand what it is that Carl's talking about. So they start by taking Lisp and rewriting it into a language which models the actor model. And they didn't fully implement the actor model, so they never did figure it out. But the language that they created was called Scheme. And they had accidentally discovered functions with lexical closure and all the stuff that we've been working on today. So the fact that you could have higher order functions, functions that return functions, and all that stuff happened by accident, trying to figure out what Carl Hewitt was talking about. And that is maybe the most important discovery in the history of programming. And as always happens, the world took no notice of it at all. And it just sat around at MIT for years and years going nowhere, and is only now, finally, after 40 years, finally coming to the mainstream. And it's coming to the mainstream because it was actually a really good idea, and its time has come. We really need it now. So the reason these things take so long, everything takes at least a generation, is because we don't change minds. We have to wait for a generation to retire or die before we can get critical mass on the next new idea. And that's the way progress goes. We imagine this is an extremely innovative industry, and in some ways it is, but in some ways we're just like everybody else. So I lived through the GoTo thing. I remember when that was happening, and all the arguments, and they were really emotional, angry arguments. And all the arguments were from emotion. There was very little argument from fact. And it just went on and on and on and on. And then it got quiet. It was like, are they gone? Can we get rid of the GoTo now? And we did. We got rid of it, and it's gone. And we're not missing it. And all of the promises that the world was going to end if we took rid of GoTo, or the lives of programmers are going to be made more miserable. None of that turned out to be true. We're not missing it. We're doing great without it. In fact, some of our languages have maybe a little bit too much GoTo left in them, but we're getting by. So it turned out we never needed GoTo. Don't need it. We're doing better without it. And in fact, what actually happened was, by getting rid of GoTo, it made it easier to write programs of greater complexity. Because if your only control construct is GoTo and conditional GoTo, there's a limit to how complex a program can get before it becomes unmanageable. And by getting rid of GoTo, we could do better with larger programs, and we could do better at achieving our ambitions in terms of writing software. So the people who were arguing against GoTo were the people who would have benefited from GoTo. They were benefited from getting rid of GoTo, and it is always like that. I expect it will always be like that. So in looking for the next language, I'm looking for it to be different in some important ways, and I'm expecting it to be crucified for those differences. I think of programming languages as being in two very distinct classes: systems languages and application languages. A systems language is a language that you would use for writing system stuff, something that needs to be close to the metal, like a kernel, a device driver, a memory manager, that kind of low-level stuff, and nothing else. Everything else should be written in application languages. Now, we need a new system language. Our dominant system language is still C, which comes from the late 60s. That was a long, long time ago. We seem to have lost the ability to innovate in system languages, and it's not like we don't need them anymore. I think we need a better version of C, but it's a long time coming. But I'm more concerned with the application languages, because that's where we all live, and we need better application languages. I think a mistake that you can see in lots of languages is that they're confused about which side of this line that they're on. For example, for my money, the biggest design error in Java was it couldn't decide if it wanted to be a system language or an application language. And one of the signs of that is that it requires the use of threads at the application level, which I think was a tragic mistake due from that confusion. So you can take the application languages and divide them into two classes. There's the classical school and the prototypal school. And for a long time, I've been an advocate of the prototypal school because of the obvious problems that are in the classical school, that you've got the classification and taxonomy problem that we talked about earlier. Back when the GoTo argument was going on, maybe at its loudest, someone published an article saying we should also eliminate the come from statement. It was a joke. And there were people who attempted to design programming languages based on the come from statement. But it turns out we have come from statements in our classical languages, except we call it extends. And what it does is cause coupling of things. And coupling can be a problem. When you couple things together, then one becomes dependent on the other. You cannot change them independently anymore. And that causes systems to become brittle. And that happens in class systems. And so the big advantage in prototypal systems is we eliminate that coupling, or we at least reduce it significantly such that that no longer becomes a problem or a barrier to progress. So I was a big advocate of prototypal inheritance. Since then, I've changed my mind. The biggest benefit you get from prototypes is memory conservation. And I think that might have been important, probably was important. Well, maybe it wasn't important in 1995. It's not so important now that we've had memory has become so abundant. You now have gigabytes of RAM in your pocket. I mean, you just can't imagine that much memory. You really don't understand numbers that big. But we still think about memory as though it's doled out in K. So yeah, it may have made sense then, not so much now. It also is a source of confusion, that we have own properties and inherited properties, which for some purposes act the same, but for some purposes don't. I'm looking to get rid of all sources of confusion, as you know, because confusion causes bugs and exploits. It also provides retroactive heredity. that you can change what an object inherits after it's constructed. I've not found any good uses for this, but I can imagine a lot of really bad uses for it, and it's something that is provided by this architecture. One bad thing about it is that it is performance inhibiting. So JavaScript engines go fast by making assumptions about the shape of objects. And they have to be pessimistic when it comes to prototype chains, because a prototype chain can change its contents at any time, and they need to be prepared for that, and that slows things down. So I used to be in favor of prototypal inheritance. I'm now in favor of class-free object-oriented programming. I think class-free object-oriented programming is JavaScript's gift to humanity. I think that's why this is an important language. It's why I hope it becomes an influential language. So let's review this again. So this is block scope. And we've got functions which have the same scope relationship. And we've got our closure again. And we've got this really important form where we have a function that returns a function. And this is, I think, the best, most important discovery in the history of programming. And we have it in this silly little language. So to review one last time, this is the model that I recommend for doing class-free object-oriented programming using functions in JavaScript. We've got a constructor which takes a specification object. We make our instance variables which we can initialize from the specification object. We get other methods or other functions that we can use that we can get from other constructors, and we can call as many of these as we like. We then create our methods which will close over all of the members, all of the other methods, all of our methods, and the specification object. And any of these which need to be public, we will put in the outgoing object, which we then freeze. By doing this, we get an object which has a hard interface, an uncorruptible interface. It will always work exactly the way it should. It cannot be confused. And it also corrects, I think, a problem that we've always had in objects, in that some things you want to access through a method and some simply by poking at the properties. Except if you allow people to poke at the properties, then there's no defense against inconsistency. Everything, all changes, at least to the object, should go through the interfaces. I made a bug once, and I need to confess. I need to come clean and share this with you. It was in 2001. And I was writing in Java. I wrote one of the first JSON parsers, and it was part of a reference implementation to show people how easy it was to write a JSON parser. And it included this statement, which created an index variable which counted characters into the string or stream that was being parsed. So if there were a syntax error, we could tell you at what character position that error occurred. And an int is big enough to cover, what, about 2 billion characters, which is pretty big. That was 2 gigabytes was a big disk drive at that time. And the way I was using JSON, I never had a message that was bigger than a couple of K. So I thought, that's a lot of headroom. That's being pretty generous. I'm future-proof that this is good. So a couple years ago, I got a bug report from somebody who had passed a JSON text to the parser that was several gigabytes in size, that contained a syntax error past 2 gigabytes. And the error message that my parser provided was wildly wrong. And they looked at the code and they very quickly figured out why it was wildly wrong. And it was because I said int. So I hate int. Int's terrible. Int, I think, is one of the worst ideas in the history of programming. And the reason I hate int is because of what it does on overflow. So if you let's talk philosophically. So what should happen if you have a value that's too big to fit in a cell of memory? What should happen? There's one school of thought that says, well, the CPU should halt. That's kind of old school. You're not going to get 9 nines that way, but at least you're guaranteed you're not going to create any bad results, right? Death before confusion. There's another school that says, we'll have an interrupt. We'll raise an exception. We'll go to some other path which says something, do something about that, give some warning, and prevent the original operation from following through. That's reasonable. Another approach would say, we'll provide some sentinel, some NaN value, and put that in memory instead. So when you go back and look for it, it'll say, I don't know what you're looking for, but it's not here. Another approach might say, take the largest thing that does fit and put that in there instead. It's called saturation. That's a reasonable thing to do in computer graphics and signal processing, but you don't want to do that in financial applications. No. But suppose what you want to do is maximize the likelihood and effect of errors. I think what you want to do is throw away the most significant bits and don't tell anybody. And that's what we do. And I don't think it makes sense. So why do we do that? It's because it made sense in the 50s. So in the 50s, we made computers out of vacuum tubes. And vacuum tubes are big, and they consume a lot of power, and they get hot, and they burn out quickly. So the more tubes you have in your ALU, the more it costs to build, the more it costs to operate, the more it costs to maintain, the shorter the mean time to failure. So if you can figure out a way to take some tubes out, that's a huge win. And some genius, and I do believe he was a genius, figured out that if we use complement arithmetic instead of signed magnitude, we don't have to implement the subtract circuit. All we have to do is put a complement, which is almost free, in front of the add circuit and ignore the overflow. That was brilliant. That was a great idea at the time. But since then, Moore's law has gone crazy with the number of devices that are possible on a chip, and we have not reconsidered that decision that was made in the 50s. And I think we are way, way overdue on that. To make this even worse, memory used to be extremely scarce and expensive. A machine might only have a couple of K in it. The Atari 2600, if you remember, only had 128 bytes of RAM. That was all of the RAM in the entire machine. So you were really careful in allocating memory to numbers, right? And if you could figure out a way to get 2 numbers into 1 byte, you would do it because you didn't have very many of them. And our programming languages are still in that mindset. So for example, in Java, you've got byte, char, short, int, long, float, and double, just as the main built-in types. So every time you create a property or a parameter or a variable, you have to ask, which one of those? You got to pick one. And if you get it right, then okay. But if you get it wrong, the program's going to fail. And it's not going to fail immediately necessarily. In fact, it might fail sometime in the future. And tests cannot find that because your tests all assume a particular data model, and they are not sufficient for finding these sorts of errors. Tests fail on this stuff. And there's no value in having picked the right type, because I saved 16 bits on this variable. Hey, what's the cache value of the savings of that memory? The answer is 0. In fact, it's nothing compared to your time. The time you spent wasted trying to decide which type is infinitely more valuable than the value of the memory that you're saving. Now, JavaScript, on the other hand, gets it right because it only has one number type. That means it's impossible to make an error by picking the wrong number type. And that's a huge win. I'm totally in favor of that. The only problem is it's the wrong type. And you know why it's the wrong type? It's because 0.1 plus 0.2 is not equal to 0.3. I've heard from some people who say that doesn't matter, and they are absolutely wrong. That matters a lot. So how did this happen? How did we get to this place? Well, again, we go back in time. So In the 40s, when the first von Neumann machines start coming online, they are integer-only machines, but most of the programmers are mathematicians, and they're trying to figure out how to do real computation, and it's hard. They're trying to do stuff with scaled integers, and it's a lot of work, and it's error-prone. And someone who is really smart figures out floating point, that we will have two numbers per number. One is the number itself, and the other is a scale factor, which tells us how many positions to move the decimal point. And then we can just give it to a subroutine, and the subroutine will figure out how to add these things. And it worked, and it made programming much easier to do. Unfortunately, those libraries were really slow. So when we get to the 50s, there's now interest in putting floating point into hardware. But we're making stuff out of tubes, and it's hard to do. And some genius, and I do believe he was a genius, figured out that if we use binary floating point instead of decimal floating point, we don't have to implement a divide by 10 in order to do scaling. We can just shift one bit, which is free. And so they did that. Now, that worked great for scientific computing, because in scientific computing, your low-order digits are probably wrong anyway, so the fact that you can't exactly represent the decimal digits is not all that important. But it doesn't work for business processing, because they're adding up money, and they need to be exact. They have to get the cents exact. So there's this division. There's scientific computing, and there's business computing. And they use different hardware, they use different programming languages. So when you order your mainframe, you either get the floating point package or you get the BCD package for doing your COBOL processing. And that's sort of the way the world worked until we kind of came into the modern age, and COBOL dies off, and Java is the successor to COBOL. But Java comes from the Fortran school, not from the COBOL school, and it doesn't do a good job of dealing with the business types, but that's kind of the tragedy that we're in now. So I propose to fix it, and this is my solution. I call it DEC64, and it's a 64-bit quantity containing two numbers modeled very much after what they were doing in the 40s. So I've got one number, which is the coefficient. It's 56 bits long. And I've got another number, which is the exponent, which is 8 bits long. And it's really nice. So you can, and it works because of this 10. So it's really easy to see what something's going to do. It's just this formula, really, really simple. No complicated packing or unpacking. I put the low order 8 bits in the bottom because on Intel architecture we can unpack that for free. So a software implementation can be very efficient. And this gets us 16 or 17 decimal places, very accurate. We can do exact business processing. It's not bad at doing scientific processing either. So my proposal is that this be the only data format in future application languages. That we just have one number type and it be this one. So to prove it, I have a software implementation available in x64 assembly language that's on GitHub. If you're curious about this, you can check it out. And it performs pretty well. So if you're adding integers in a software implementation, it can add 2 integers in 5 instructions, which is pretty good. It's maybe 4 more than you'd like, except that with those 5 instructions, you also get overflow protection and you get nans, which are nice things to have, I think essential things to have. In a hardware implementation, adding integers should happen in 1 cycle, which means we don't need to have ints as a separate type in order to get performance. We can get performance and we can get the range of values that we need in 1 number type. So my goal is to convince everybody in the world that this is the 1 number type to use in the next system. Now, it turns out I don't actually have to convince everybody in the world. I only have to convince one person. That's the man or the woman who designs the next language. If I can convince that person that they want a language with 1 number type that works well with humans, that does arithmetic the way we were taught to do arithmetic in school, so that we won't get confused, then we'll win. Turns out I have a little bit of experience at convincing everybody in the world to do the right thing. For example, there's the JSON data interchange format, the world's best loved data interchange format. It took a while to convince everybody, but eventually everybody got on board and the death threat stopped, and we're all happy about it now. I'm very happy to report that this took much less than a generation. This is one of those very rare things where we were able to move it in just a few years. So if you look at Google Trends and compare the trends of JSON versus XML, you'll see that the world has steadily been losing interest in XML. Well, it looks like the years are chopped off here, but it's on the other screen. Since 2005, the world has steadily been losing interest in XML, and we've slowly, quietly been seeing interest in JSON creeping up. And this increase was not motivated by any industry. There is no JSON industry which drives this, because all the tools are free and simple, and so it's just happening because you decided this is a better way of doing things, and so it's just taking up. So I can't predict when these lines cross over, but Google can, so it looks like next year, for sure, JSON becomes officially more interesting, according to Google, than XML.
But in terms of use, we're using JSON more across, as a data interchange, there's more people using JSON, right?
I have no way of knowing. It seems like that to me too, but
I think they're just Googling XML because it's still difficult and we don't have to Google a JSON so often because it's easy.
I think there's a lot to it there. Yeah, so a lot of the, like if the search suggestions, XML sucks, that's a popular thing. You don't see that on JSON searches. So there may very well be something to that. So I did not intend for JSON to be the last data interchange format. JSON was intended to do a very specific thing of allowing applications written in different languages to be able to communicate with each other over the internet. But JSON is now being used for lots of other things that it wasn't necessarily designed for. And so I expect there are going to be other data formats as well. So I have some advice to anybody else who might be designing another data format. Number one, please don't break JSON. JSON is working really well for the thing that it was originally designed for. One of the best things that I did in JSON was I did not put a version number on it. So there is no way to revise it. We can't say JSON 1.1 because there was no JSON 1, it's just JSON. So the way it is the way it will always be, which is great because if you look at the stack, I expect over the years, the stack is going to be changing all the time at every level, except in the JSON layer. The JSON layer will always work the way it does right now. And that's a pretty nice thing. Having that level of reliability and integrity in anything in the net is huge. I can't think of any feature we could add to JSON which is more valuable than that. So if you want to make something else, please make something else and make it better, but don't try to break JSON. Leave JSON alone. Whatever you're going to do, if you're going to do something that's kind of like JSON but different, make it significantly better. If it's just JSON with one or two little things, then what you're doing is you're adding a compatibility hazard to the world that people are going to have to deal with this thing which is kind of like JSON but isn't. And so there's a cost to that. So make sure the cost is worth it. Add enough value to it to justify that cost. And, get a better name. Because no question, the worst thing about JSON is the name. For one thing, people are confused about how to pronounce it. I say JSON, a lot of people say JSON. It turns out the correct pronunciation is JSON. Everybody? JSON. Yeah, so, and I hear from guys all the time named Jason saying, I'm in the office and I hear someone go, what? Yeah. So, I'm sorry, Jason, if you're here. I don't know what I was thinking. Sorry. So, I've heard from guys named Jason who threatened to make new standards called Douglas. So, just to show me what it's like. But again, the worst thing about JSON is the name. It stood for JavaScript Object Notation, and almost everything about that is wrong. So I called it JavaScript because I wanted to give credit to JavaScript, because that is where the idea came from. I didn't invent JSON. I discovered it already in this language. And I was trying to give respect to it. I was not trying to jump on JavaScript's coattails, because I'll tell you, in 2001, JavaScript was not a much loved language, right? And saying, I'm JavaScript, you know, that's not a way to get credibility from anybody. I was just trying to be honest. I was just trying to, you know, recognize where it came from. But the name is problematic. For one thing, people still don't know what Java is versus JavaScript. I mean, that stuff is still going on. And also there's a confusion that, so JSON only works with JavaScript? No, that's not true. That was never true. There's also a confusion that, I guess the JavaScript language standard is what defines JSON, and that was never true. But there are all these confusions that happen because I chose the wrong name.
What should you have called it?
I don't know. It's
You thought about it?
that boat has sailed. We're done. Then there's object. Object here represents the way that JavaScript thinks about objects, right? Just a loose collection of key value pairs. That's an object, which is not the way most languages think about objects, right? They have this more brittle thing. We got classes and instances and so on. So they get confused, you know, that we can send them a JSON object and they go, that's not an object, and go, yeah. Notation, maybe that's okay. So notation's bad. So if you're going to make up a new data standard, and I think you should, don't call it JSON. You know, don't stick a letter in front of it or a letter on the end of it or anything like that. You know, come up with some creativity, you know, do something good there. Let's talk about responsibility. Who are you responsible to when you're programming? Well, this is my answer. This is who I think I am responsible to when I'm writing code. My number one responsibility is to the people, to the poor bastards who have to use my software. I want it to work really well for them. I don't want to frustrate them. I don't want to confuse them. I don't want to hurt them. I don't want to lead them to ruin. I want to give them the best experience possible. I want to make their lives better to the extent that I can. We imagine in the software industry that we're making the world a better place, despite all the obvious evidence to the contrary. We really want to believe that. But we should at least try to make it true for the people who are using our stuff as they're using it. We should at least do that. I've seen teams where they have contempt for their users. They hate their users. The users are always complaining. They don't understand how to use our stuff. They don't appreciate our genius. They're stupid. They're awful people. Hate them, which I think is totally toxic, that it's inexcusable. We should never be thinking like that. Everything that we do should be in service to humanity. Number two, the team. I want to be writing the best code that I can, the clearest, best, well-documented, easy to understand, good code, because other people who I'm going to be working with are going to have to take that code and make it better. And I don't want to be setting them up for failure. I don't want to be frustrating them. I don't want to be making their lives worse. I want to make their lives better. I want good code for everybody, and I expect them to do the same. So programming can be a solo activity, but generally we're trying to do stuff which is so complicated and we're trying to do it so quickly. We're working in teams almost all the time, and sometimes big teams. And in large literary efforts, there's this idea of writing with a single voice. Like if you're writing an encyclopedia, or if you're a couple of authors writing a book, or if you're writing a magazine, or some other thing where you've got lots of writers working on the same project, they're all trying to write in the same voice. And that doesn't interfere at all with being able to express good ideas and presenting it clearly. And I think we need to be doing that in writing software too. So I want us to be writing all in the same voice. And that voice is the smartest, most professional programmer who has ever lived. I want everybody on the team to be writing up to that level. I don't want anybody dumbing it down because they think they need to express themselves by leaving out their semicolons. I want everybody to be writing really well. Then number three, management. If they ask for it and it makes sense, okay, we'll do that too. Now some managers might be saying, whoa, wait a minute, we're supposed to be in charge here. Shouldn't we be number one? And I don't think so. I think number 3 is the right place for them. So if you look at what a CEO does, one of their most important responsibilities is to help the company look out. There's a tendency in a company, especially as they get bigger, that everything is focused inside. There's competition for resources and attention and promotion and all of that stuff. And you tend to forget about the customer, and you tend to forget about the marketplace and all these really things that are actually much more important than what's going on inside. And part of the CEO's role is to remind the company of that. And you see CEOs always saying things like, be the customer and be customer focused and all of that stuff. That's what that's all about. And that's very compatible with what I'm saying. I'm saying number 1, the people. Then one of the biggest problems that companies have is that their code bases are awful, that they're full of cruft, they're what they call legacy, it's just awful stuff, and that seriously impairs the company's ability to compete. That you can't make changes, you can't extend, you can't grow, because the software is holding you back because of its poor quality. So the software becomes a liability rather than an asset. And I think we can change that if we're writing high quality software for the team. We allow the company then to be much more competitive, much more responsive, much better to serve the market. So suppose you're writing your own software. You're at home and you're doing your own stuff. What are your responsibilities then? Number 1, still the people. I mean, assuming that someone else is ever going to have to write your stuff, you really should write it well. Write it for them, whoever they might be. Even if you don't know who they're going to be, you should still have somebody in mind when you're writing this stuff. And then number 2, the team. If you have any ambition of this stuff getting good enough that you might want to open source it, that means your team is now potentially every programmer in the world. So make it good for them. And then number 3, your management, so knock yourself out. So that brings us to the end. I can't think of anything else to tell you. So thank you all very much. But before we go, I've got one piece of advice. This is really serious, and I hope you don't forget this. I'm really serious now. Please don't make bugs. Thank you.
We got a couple random questions from chat. I'm not sure if you want to take any more questions, but
Are they good?
well, it's just kind of opinions on Swift.
I don't have an opinion on Swift.
TypeScript.
Mate,
I'm sorry?
How about your opinion on TypeScript?
On TypeScript. I see TypeScript as a trap. It keeps you in the classical model. You'll never figure out functions if you're locked into TypeScript.
there's a question about being able to freeze data objects.
You can. I don't recommend it. Unless you have something that really wants to be immutable. Remember that once you freeze something, you can't unfreeze it. So you're only going one way.
And then, let's see, dates in JSON.
Nope, JSON's done.
Yeah. Well, no, okay. So you just don't have a recommended format?
JavaScript didn't have one, so JSON didn't get one.
Unix timestamp.
Yep. I'd recommend using ISO strings. That seems to be the smartest thing. I know there are a lot of people who don't like doing smartest things, so they're free to do whatever they want.
What's your take on the JSON API spec that's been going around recently?
For Java?
No, it's Ember has embraced it as being kind of the way to format JSON packages for sending back and forth in the server. It's basically a collection of how you organize the data inside of JSON, inside your object.
I'm not aware of it. Anybody's free to do anything they want.
Except make bugs.
No, unfortunately, they're free to do that too.
Why don't you have an opinion on Swift? Have you just not looked at it enough, or?
I've not looked at it enough. I went to get the Swift report, and it was hidden behind some Apple login thing, and said, hell with that, so I didn't get it. So I'm not up to date on it.
Is there a reason you don't use camel case? Use snake case?
So there's this big debate. What is the correct way to do multi-word identifiers in any language? Should you use camel case or should you use underbars? And this is another one of those things that programmers can't agree on, that there's an endless argument. And the reason there is an endless argument, why it will never end, is because they are both wrong. That the correct thing should have been to use space. That our languages only have to get a tiny bit smarter, and we could have spaces as valid characters inside of names. And then they would read better and they'd be easier to process and all of that stuff. So one of the aspects I'm looking for in the next language, besides getting numbers right, is that it'll also allow space as a component of names.
Thoughts on Angular or Angular 2?
Thoughts on Angular or Angular 2? That's two completely different questions.
Either or.
I've looked at Angular and I was kind of surprised at how hard it is to make something easy. I don't get it. I hear from people who swear by it, and I think that's great. And maybe it solves the problem they have. I've not observed that it solves a problem that I have.
It's the Stockholm thing, I think, with Angular. Once you get there, this is great.
Well, the problem with all these frameworks is that once you get committed, you are stuck. You can't go, ooh, that was a mistake, and back off. You're fully committed. And so you can't find out if any of these things are good or not until you commit. And so you have to be careful.
So I went from GitHub to douglascrawford.com, and you clearly have no load CSS. And I don't think there's any CSS on there. Maybe I'm wrong. Why?
What?
What's your issue with CSS?
Oh, you're going to bring up that old wound again.
Sorry, yeah.
So CSS was designed for formatting technical documents. That was its purpose in life. And that is not what we use it for. We use it for all kinds of stuff that is very badly suited for. And we use it because it's the only option. And it's better than it was before it came along, because in the past there were no options. Used to see people doing typographic spacing by having tiny little GIFs that, with a little bit of white space in them, which was considered a best practice in the day, but was always a terrible thing to do. So compared to that, CSS is great, but compared to what we deserve, it's awful.
You can say the same of HTML, right? I mean,
yeah. That too.
Yeah.
Any opinions on the Rust language?
No, I don't. I have read some of their material. It wasn't locked behind an Apple password, so I have read some of that. And some of it looks promising, but I don't have any conclusions yet. I've not worked with it.
What about transpilers? And do you have any recommendations or?
So let me say this about CoffeeScript, which started this craze. I like CoffeeScript a lot. CoffeeScript makes some of the good parts of JavaScript more visible. For some people, it's easier to learn how to use JavaScript well if they learn CoffeeScript also. I think the thing I like best about CoffeeScript is that it doesn't look like C or Java or any of those other languages. It's got its own look. It used to be said that no new programming language could succeed unless it looked like C. And CoffeeScript is showing that that's no longer true. CoffeeScript succeeds because it doesn't look like C. So I like that a lot. Then the question is, should you use CoffeeScript in production? Absolutely not. No, you should not use CoffeeScript in production. It's still an experimental language. It adds a lot of weirdness. It makes it harder to recruit people because, who's going to write the CoffeeScript stuff that some hipster left? It's just not worth it. So I always recommend learn the language, pick up a new language, and some of the transpiled languages are interesting and are worth study, but I don't recommend using any of them in production. I think they don't add enough value to justify the weirdness.
Lots of thank yous, and please extend our gratitude for the training. Do you find any more?
Yeah, somebody's asking, is there a reason that you disabled bug reports on your GitHub projects?
I didn't do that. What I have complained to GitHub that there is no. I'm trying to think of the right way to say this. I tend to attract trolls. I don't know why this is, but there are a lot of people who really want to come onto where I am and do trollish behavior, which is more than annoying. It's a waste of time. I have to deal with the trolls, and I don't like having to do that. So I've asked GitHub for a no troll option, and so far they have not figured out how to implement that. So there are some things that I've turned things off, but it's not completely off. You can still get messages to me. But if you have trolled me, I put you on the block list, so that may be his concern. He may have trolled me in the past and he can't troll me now. So I'm not going to apologize for that.
Did you have any opinions on build systems? On, you mentioned practices of concatenating, minifying, and all that stuff. Like they're saying things like Webpack or whatever.
No, I don't care. Whatever works.
Yeah, that's what I figured. Not seeing any other questions. Anybody in the room? It's your last chance to get an opinion. All right.
Okay, I think we're adjourned.
We'll conclude it. All right.
Thank you.
Yeah, thank you.